In just 200 seconds, a 53-qubit quantum computer did what every classical machine on Earth would need 10,000 years to finish. It didn't just run faster, it's as if it borrowed time, space, or something far stranger. If that speed-up only makes sense because the calculations spilled into many worlds, then where did the extra reality come from? And why would any advanced civilization ever stay trapped in this one? Somewhere in our equations, a door has started to swing open, and it does not lead outward into space. It leads inward into the machinery that decides what counts as real. For a century, quantum theory has been the most accurate story we have. Yet, it has never been a comfortable one. We learned to calculate with it, to build lasers and transistors, to split atoms and map the chemistry of life. But we also learned to avert our eyes from a deeper question. What exactly is doing the work when the universe computes? Because that is what the latest experiments force us to consider, not as philosophy, but as engineering. In laboratories sealed against vibration and light, matter is cooled until it forgets almost everything, and a few delicate degrees of freedom are persuaded to behave like a single, coordinated object. The result is not merely a faster calculator, it is a device that seems to access an accounting system classical physics cannot even describe. If reality is built from particles in space, then every computation should ultimately be paid for in ordinary resources: time, energy, memory, and heat. Yet quantum computation keeps hinting that the true budget is stranger. Coherence that must be protected, phases that must be aligned, correlations that must be maintained against an environment eager to take a copy. And when those correlations survive, the output carries a distinctive statistical signature, like a receipt printed by nature itself. That receipt is the unsettling part. It suggests that the place where the computation happens may not be inside the chip in any familiar sense, and that the stage we call space-time might be only the surface of a deeper ledger. A ledger where information is not what we store in the universe, but what the universe is made of. In this documentary, we follow that trail from a small superconducting circuit to the oldest dispute in quantum mechanics. Why measurement yields one outcome when the equations describe many. We meet the physicists who refused to add a magical exception for observation, and the ones who tried to make peace with that refusal by explaining how worlds become separate without ever being chosen. And then we ask the next question that inevitably follows. If separation is really about information flow, what happens when a civilization learns to control that flow with precision? Along the way, the story changes scale. The thermodynamics of erasing a bit becomes a clue about the cost of thought. Black holes become not just cosmic disasters, but bookkeeping devices with boundaries that behave like memory. And entanglement, once treated as a bizarre link between particles, begins to look less like a feature of space and more like the scaffolding from which space is assembled. By the time we return to our own sky, the mystery has shifted. The silence between the stars may not be emptiness at all. It may be what you should expect if intelligence learns that the physical cosmos is a crude interface and that the most valuable territory lies elsewhere. Not in distant galaxies, but in deeper layers of computation where heat is scarce, errors are corrected, and reality can be partitioned and rejoined. This is an exploratory journey through quantum speedups, many worlds, information physics, and the geometry hidden inside entanglement, pursuing one unsettling possibility: that the horrible thing quantum computers reveal is not a new threat, but a new address for where the universe keeps its power and where advanced minds might choose to live. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We will move from a laboratory anomaly to the origin of quantum computation, then descend into information, horizons, and entanglement-built space-time. And at the end, we will confront what that implies about where everyone is and what we may be building without realizing it. In 2019, a quantum processor finished a task in about 200 seconds, and the number landed like a dare. The same task was estimated to take a top classical supercomputer around 10,000 years, even with careful engineering assumptions. That gap is the opening anomaly of this story, because it looks less like progress and more like a rupture. On screen, it reads like a simple race, but the race is not fair in the usual way. One machine is a cathedral of silicon, fans, and power lines built to push classical bits through deterministic steps. The other is a quiet slab inside a cryostat, wires descending like vines into a cold darkness, where the computation is a controlled quantum evolution. The claim was called quantum supremacy, a loaded phrase for a narrow milestone that still carried symbolic weight. It did not solve climate models or discover a drug on camera, and it did not crack a bank vault while reporters watched. It produced samples from the output distribution of a random quantum circuit, which sounds almost like a trick. The result was a list of bit strings that looked meaningless, yet carried a signature. That signature was statistical, not semantic, and that is the point being tested. Quantum mechanics predicts a very specific distribution for that circuit, down to subtle biases in which bit strings appear more often. A classical computer can generate bit strings too, but matching the quantum distribution is the hard part. The difficulty scales brutally as the circuit grows, because the distribution is shaped by interference patterns that are expensive to track. This is where the stakes become physical, not rhetorical, because the output is not an opinion. If the distribution is correct, the device is doing what quantum theory says, at least within the measured error bars. If the distribution is correct and classical simulation is infeasible, then something in nature is computing beyond our usual accounting. The output becomes a receipt from reality, signed by physics. To understand why sampling matters, we need a brief detour into what hard means in this context. The circuit is not designed to yield a human-readable answer, like a sorted list or a decoded message. It is designed to generate a fingerprinted randomness, where the randomness is structured by the circuit's quantum dynamics. The question is whether a classical machine can fake that fingerprint without paying the same underlying cost. The machine had 53 qubits, a number small enough to fit on a slide and small enough to sound unimpressive. Yet each qubit was not a simple on or off switch, and that difference is everything. A qubit is a quantum system with two basis states, often labeled 0 and 1, and those labels are only the endpoints. Before measurement, it can occupy a superposition, described by probability amplitudes that carry both magnitude and phase. Amplitudes are not probabilities, and that distinction drives the whole mystery with almost cruel elegance. Probabilities add like ordinary chances, and they never go negative, so they cannot erase each other. Amplitudes add like waves, and waves can cancel when their phases oppose. Interference is the rule that turns many possibilities into one observed outcome, and it is also the rule that makes the bookkeeping explode. If you want a visual, imagine ripples on a dark pond, crossing and reshaping each other in real time. Some crests reinforce, and some crests vanish into flatness, and the final pattern is not a simple sum. In a quantum circuit, those ripples are complex amplitudes, rotating in an abstract space, and the flatness is a probability driven towards zero. The computation is not just exploring options, it is pruning them through cancellation. A quantum circuit is a sequence of gates that reshape those amplitudes, one calibrated interaction at a time. Gates are controlled physical operations, timed and tuned with extreme precision because phase errors accumulate like tiny misalignments in a telescope. They rotate states, entangle qubits, and spread amplitude across an exponential space that no camera can directly film. After many layers, measurement collapses the state into one bit string, and the richness is hidden in the statistics across many runs. Entanglement deserves a slower sentence, because it is the hinge of the whole story. When qubits are entangled, you cannot fully describe each qubit on its own, even if they sit millimeters apart on a chip. The information lives in correlations, not in the parts, and those correlations are what make the state space feel so large. In plain language, the system behaves like a single object with many degrees of freedom. The task in 2019 was to run such a circuit many times and collect samples, like drawing from a peculiar deck. Each run produced one bit string, and the set of samples approximated the circuit's output distribution. The circuit was random by design to prevent clever shortcuts, and random here means pseudo-random gate choices that still obey hardware constraints. The goal was not usefulness, but hardness. Hardness here means classical simulation requires resources that explode with qubit count and circuit depth. And the explosion is not metaphorical. To compute exact amplitudes, a classical machine must track a vector with two Gaussian complex entries, and each entry needs memory and arithmetic. For n equal to 53, that space is astronomically large, and astronomical is not just a flourish. Even storing the full state naively would demand memory on a scale that strains the world's largest machines. Approximations exist, and the classical community is good at finding them, sometimes with startling creativity. You can exploit circuit structure, compress tensors, or trade exactness for a controlled error, and those strategies can shrink the gap. Yet the circuit was chosen to frustrate the most obvious compressions by mixing qubits and spreading entanglement across the chip. The intent was to create a chaotic enough evolution that the simulator can't find a clean handle. The 10,000-year estimate was debated, refined, and challenged, and that debate matters for the tone of this documentary. Better classical algorithms reduced the gap, and hardware improved too, which is exactly what science should do under pressure. Yet the core lesson remained that scaling laws diverge, even when the headline number shifts. Quantum growth is exponential in state space, while classical tracking pays the full price of that exponential bookkeeping. There is also a historical echo here, because computing has seen impossible become routine more than once. Early classical computers were once dismissed as toys, and then they quietly reorganized economies and warfare. But this is not a story about a faster chip, like a new GPU, where the same logic runs with more transistors. It is a story about a different kind of bookkeeping, where nature seems to store and update information in a space we cannot directly access. The question is not how fast the device is, because speed is only meaningful relative to a model. The question is what physical process is doing the work and what resource is being spent. In classical machines, the resource is straightforward: bits in memory, gates switching, energy dissipated as heat. In quantum machines, the resource looks like coherence and interference, and those are not commodities we can weigh. The processor itself was a character with contradictions, and the visuals almost write the metaphor for us. It was delicate, noisy, and prone to error, built from superconducting circuits that behave quantum mechanically when cooled. It had to be cooled near absolute zero to preserve coherence, because thermal motion is a vandal that smears phase information. It required isolation from stray fields, vibrations, and heat, and the lab becomes a kind of monastery for fragile states. Inside the cryostat, the chip sits like a small city seen from above. with patterned metal traces and junctions that act as non-linear quantum elements. Above it, coaxial cables and attenuators descend in stages, each stage colder than the last, filtering noise from the warm world. The refrigerator is not decoration, it is part of the computer, because temperature is part of the error budget. Even the vacuum and shielding are computational infrastructure. Noise is not a footnote, because noise is the enemy of the miracle, and it attacks in several ways. Decoherence scrambles phase, relaxation leaks energy, and control errors tilt rotations by a few degrees. And those few degrees compound. If the device were merely random, its samples would not match the predicted distribution, and the fingerprint would wash out. The experiment used cross-entropy benchmarking to compare outputs with expected statistics for smaller circuits, where classical checks were still possible. Cross-entropy benchmarking sounds abstract, but the intuition is concrete enough to narrate. If you know which outcomes should be more likely, you can score how often the device lands on them, even if you cannot predict every run. A perfect quantum device would concentrate probability in a pattern that matches the ideal calculation. A noisy device drifts toward uniform randomness, where every bit string is equally likely, and the score collapses. The match was imperfect, but it was not arbitrary, and that is where the tension lives. The system was noisy enough that it could not run indefinitely, yet coherent enough to preserve a non-trivial interference pattern. It could not be perfectly controlled, yet it was controlled enough to keep the distribution's shape. It sits on the edge of decoherence and still pushes through, like a signal carried across a storm. At this point, the documentary's mystery takes shape. When a classical computer struggles, we can point to memory limits, clock speed, and energy, and the explanation stays inside the box. When a quantum computer succeeds, the explanation is not just faster switching or better parallelization. It is interference guiding amplitude through an enormous space, and then compressing that evolution into a single observed sample. But what is that space, physically? And what does it mean to say the system explores it? In the math, the state lives in a Hilbert space of dimension, 253, and the vector evolves smoothly under unitary operations. In the lab, we see only 53 components on a chip, plus control electronics and refrigeration. The device behaves as if it navigates a combinatorial universe, then returns with a single bit string like a stamped passport. One safe answer is that quantum mechanics is simply the correct rulebook, and we should not demand a picture beyond the equations. The amplitudes are not places, they are numbers, and the machine is just obeying Schrödinger's equation under carefully engineered Hamiltonians. Yet the equations describe parallel possibilities evolving at once, and the engineering works because those possibilities interfere. The safe answer explains the prediction, but it does not satisfy the curiosity the prediction awakens. This is where interpretation stops being academic, because the device turns metaphors into hardware requirements. If the computation depends on many simultaneous branches, then we must ask what those branches are, and whether they are merely counterfactual. Are they bookkeeping devices in our heads, or do they correspond to real physical histories that exist somewhere in the ontology? The 200-second result pressures that question because it makes the as-if sound less optional. The many worlds interpretation offers a blunt picture, and bluntness can be clarifying. The wave function never collapses, and every outcome occurs in a branching multiverse, with observers finding themselves in one branch. A quantum computer would then be a device that spreads computation across branches, while remaining one coherent wave function. Interference would be the mechanism that recombines branches to amplify the right answers and suppress the rest. That picture is often dismissed as philosophy because it seems untestable and because it offends a certain taste for single outcomes. Yet quantum computing turns it into an engineering narrative, where coherence time and gate fidelity become the practical language of branching and recombination. The speed-up looks like extra work done somewhere we cannot see, because the classical simulator cannot keep up. If many worlds is correct, the extra work is not metaphorical. It is distributed across real branches. The horrible implication is not that parallel universes exist in a sci-fi sense, with portals and travelers. The implication is that our familiar universe is not the whole computational substrate, and that what we call one outcome is a local perspective. If the only coherent explanation is many worlds, then the machine is not simulating parallel realities. It is interacting with them, and the interaction is as mundane as a calibrated microwave pulse. There are other interpretations, and we will treat them seriously, because the documentary is not a recruitment poster. Some keep a single world and add hidden variables, or modify collapse, or treat the wave function as information rather than substance. Yet each alternative must still explain the same empirical fact without hand-waving away the scaling. A small, cold, noisy device produced the right statistics at a scale that breaks classical accounting. So the documentary will not ask whether quantum mechanics is true, because the experiment is already a vote in that direction. It will ask what quantum mechanics is saying about what exists and what it refuses to say. It will ask why computation seems to access an exponential resource without paying an exponential cost. At least, not in the way classical machines pay. It will ask whether reality itself is the computer, or whether computation is simply what reality does. This matters beyond physics, because computation is a measure of what can be done, and what can be done becomes what will be attempted. If quantum speedups are real and scalable, then the limits of technology shift, even if the first demonstration was deliberately useless. Encryption, chemistry, materials, and optimization become different landscapes because the cost of exploring certain spaces changes. More unsettlingly, the boundary between physical law and information processing dissolves, and we are forced to speak in a mixed vocabulary. It also matters for the far future, because advanced civilizations are constrained by energy and entropy, and those constraints are not negotiable. If there is a deeper substrate where computation is cheaper or more powerful, then the incentive is clear, and the trajectory is almost evolutionary. You would not just build machines inside the universe, you would build machines that use whatever the universe is built from, and you would treat physics as an API. For now, we stay with the first crack in the wall, because it is enough to change the room. In 200 seconds, the processor produced samples that classical machines could not feasibly reproduce, at least not with known methods and reasonable resources. The output was not a proof, but it was a trace, and traces are how science begins. It was a receipt that something enormous happened in a small place, and the receipt had the right watermark. We can call it clever engineering, and it is, because the experiment required years of calibration and error characterization. We can call it a triumph of control over quantum matter, and it is, because control is the difference between a quantum system and a quantum computer. Yet the scaling suggests more than craftsmanship, because craftsmanship alone does not create exponential headroom. It suggests that the computation is not confined to the hardware we can point at, even if the hardware is where we touch it. So we end Chapter 1 with a door appearing, where there should be a wall, and the camera lingers on the seam. The door is labeled superposition, interference, and entanglement, words that sound like vocabulary until they behave like machinery. Behind it is the question of where the extra reality comes from, and whether extra is even the right word. To understand what the quantum computer is doing, we must revisit the argument that made parallel universes an engineering requirement, not a metaphysical preference. The door from Chapter 1 opens onto a question that refuses to stay philosophical, because it points at hardware on a lab bench. If 53 qubits outrun Earth's classical machines, where is the work happening, and what physical thing is doing it? We can picture the experiment as a clean room scene. White lights, stainless steel, cables disappearing into a dilution refrigerator, vacuum pumps thrum behind panels, and braided microwave lines snake downward through thermal stages like roots seeking cold. Inside that refrigerator, the chip sits colder than deep space, protected from stray heat and noise. Yet the result looks like a kind of computation that should require an astronomical ledger. The mystery is not only that it runs fast. The mystery is that it runs at all, using so little visible machinery. In 1985, David Deutsch tried to answer that question before the hardware existed, when quantum computer still sounded like a metaphor. He did not start with a faster chip or a clever circuit layout. He started with a claim about physics and computation, one that forces you to ask what counts as a computational resource. In his framing, the question is not, how do we calculate, but what does the universe allow a physical system to do? Deutsch's breakthrough was to define a universal quantum computer in the same spirit as Turing, but with quantum dynamics as the primitive. He described a machine whose allowed operations are unitary evolutions on qubits, meaning reversible, norm-preserving transformations. Reversible is not a slogan here. It means the evolution can be undone in principle, step by step, because no information is thrown away. He argued that any finite physical process can be simulated by such a device, provided you can encode the relevant degrees of freedom. That move matters because it ties computation to the laws of motion, not to human notation or clever encodings. A program is not just an abstract proof written in symbols. It is a controlled physical transformation of a state, carried out by a system that obeys quantum mechanics. In that view, the boundary between physics experiment and computation becomes thinner than we like to admit. There is a quiet historical context behind that claim, because the 1970s and early 1980s were full of warnings. Physicists like Richard Feynman had argued that classical computers struggle to simulate quantum systems efficiently because the bookkeeping explodes. Each extra particle doubles the descriptive burden, and the memory cost grows like a runaway chain reaction. Deutsch's 1985 paper turns that warning into a proposal. If nature is quantum, then a computer built from quantum parts should simulate nature directly. Classical computing makes the physics to computation link feel obvious, because the mapping is visible and almost tactile. Bits correspond to stable physical states, voltages in transistors, magnetization in domains, charge on a capacitor. Gates correspond to local operations that copy, flip, and route those states, and you can trace the causal chain with an oscilloscope. You can literally watch a clock edge ripple through logic, and you can identify where a signal was delayed or distorted. The resource accounting is also visible in classical machines, and that visibility is part of why the classical story feels complete. More memory means more distinct physical configurations you can reliably store without confusion. More time means more gate operations you can apply before the answer is needed, and you can count those operations in clock cycles. Even energy shows up in a classical way, because heat is the price of irreversibility, and noise is the enemy of reliable switching. Engineers learn to read a computer like a landscape of constraints. You can point to the RAM chips, you can point to the power supply, you can point to the clock, you can point to the cooling system, and to the copper traces that become resistive losses at high frequency. The machine's limits feel like ordinary limits: space, time, and heat. Deutsch asked what the analogous accounting is for quantum machines, where the basic object is not a bit, but a qubit. The equations say the state is a vector, and the vector lives in a space whose dimension doubles with every qubit. Each added qubit does not merely add one more dial, it doubles the size of the mathematical arena in which the state can move. That doubling is not a metaphor for more possibilities. It is a precise statement about how many independent parameters you need to predict future measurement statistics. This is where the story stops being about cleverness and becomes about ontology. The formalism describes an exponentially large arena. The lab device has only dozens of components, etched into a chip you can hold between tweezers. You can photograph the chip, weigh it, and list its materials, and none of that looks remotely exponential. The arena is Hilbert space, the mathematical space of quantum states, and it is easy to misunderstand what that means. It is not a place you travel through with a camera, and it is not a hidden room behind the refrigerator door. It is the bookkeeping structure that makes superposition and entanglement precise, and it is the stage on which unitary evolution is defined. It is also the structure that makes phase a physical lever rather than a decorative number. In plain terms, Hilbert space is the set of all possible states the system can be in, together with rules for adding states and measuring overlaps. The overlaps, inner products, are what turn state into a predictive object, because they determine probabilities. When physicists say, rotate the state, they mean apply a unitary operator that preserves those overlaps. Preserving the overlap is what preserves total probability, like conserving length while turning a vector. For n qubits, the state is a superposition of two on-basis states, and those basis states look like ordinary bit strings. Each basis state corresponds to a pattern like 001 across the qubits, as if each qubit had chosen 0 or 1. The coefficients are complex amplitudes with magnitude and phase, and the phase is not decoration. Phase is the handle that lets you arrange cancellation. And cancellation is what turns many possibilities into one biased outcome. Complex numbers enter because quantum evolution is wave-like, and waves carry phase as well as amplitude. Phase is the relative timing of oscillations, but in quantum mechanics, it becomes a relative orientation in a complex plane. Two paths can arrive with equal magnitude and opposite phase, and then they cancel as cleanly as ripples on water. That cancellation is not a loss of energy in a classical sense. It is a reshuffling of probability weight across outcomes. Say it in the concrete numbers that haunted the 2019 result, because numbers are how the abstraction bites. 53 qubits correspond to 2T53 complex amplitudes. That is about 9 quadrillion numbers before you even discuss precision, error bars, or the fact that amplitudes must be normalized. Even storing them as modest precision floating point values becomes a memory problem measured in petabytes. A classical skeptic can reasonably ask what those numbers really are, because no one is printing them out. This is not many classical bits hiding inside the chip, like a secret hard drive. The qubits do not store 9 quadrillion readable registers, and there is no measurement procedure that reveals an amplitude list. The state is not a spreadsheet you can open. It is a physical condition that only reveals itself indirectly through the statistics of repeated measurements. Measurement gives you a single outcome, a bit string, sampled from a probability distribution defined by those amplitudes. If you repeat the experiment, you build statistics, and from statistics you can infer some global features. Yet the full state is not accessible in one shot, and tomography scales terribly. The power is not that you can read the whole wave function. The power is that the wave function steers the computation anyway, even while it stays mostly hidden. The amplitudes are a different kind of physical description of one system, not a catalogue of hidden classical states. They encode how the system will respond to future operations and measurements. They are the internal degrees of freedom that the unitary dynamics updates, and the update rule is linear, which is crucial. Linearity is the reason you can treat the state as a coherent whole, rather than as a bag of independent cases. Linearity means the evolution of a superposition is the superposition of evolutions, and that is the mathematical root of the many paths language. If you apply a gate to a state that is half 0 and half Dutch 1, the gate acts on both components at once. It does not choose one component and ignore the other. It updates the relationship between components, including their relative phases, and those relationships are what later gates exploit. This is where the physical question becomes unavoidable, because the formalism is not shy about what it demands. If the computation seems to require tracking 2 Hon amplitudes, then either nature is doing that tracking, or our story about what the symbols mean is incomplete. The speed-up is not a free lunch. It is a clue about what the physical substrate can represent, and about what kinds of state are allowed to persist. A classical skeptic can still say this is only math, and math can be large without implying a large reality. You can write down a huge number on paper without believing there is a huge object in the room. Deutsch's point was that computation is not only math. Computation is a physical process that must be instantiated somewhere, with causal links that produce the answer. If you claim the calculation happened, you owe an account of what actually changed in the world. Deutsch framed the issue as a demand for mechanism, not a preference for interpretation. An interpretation tells you how to talk about the wave function, and it tells you what to say happened when you measured. A mechanism tells you what in the world is doing the causal work, especially during the part you do not observe. The demand becomes sharper when the unobserved part is the part doing the advantage. In many discussions of quantum theory, interpretation is treated as optional, almost a matter of taste. You can calculate without committing to what is real, and for decades that attitude was practical. Quantum computing makes that detachment harder, because the calculation is now a machine you built, and the machine behaves as if the formalism is physically active. It behaves as if phase is a controllable resource, like voltage or time. When you watch a quantum circuit diagram, it looks like a classical circuit with exotic symbols. There are wires, boxes, and time steps, and the temptation is to imagine a hidden classical story underneath. Yet the gates are not copying and routing definite bits. They are applying unitary transformations that preserve coherence, and coherence is the fragile resource that makes interference possible. Lose coherence, and the circuit becomes, in effect, a noisy classical sampler. A quantum algorithm is not a brute force search that tries all answers and reads them out, and this is the point that often gets simplified into a misleading slogan. It is a designed interference pattern, like a carefully engineered wave experiment. The algorithm spreads amplitude across many computational paths, then uses phase to cancel most paths while reinforcing a structured subset. The structure matters, because arbitrary problems do not offer the symmetries that interference can exploit. Interference is the engine that replaces naive parallelism, and it is also the reason quantum speedups are rare and delicate. Wrong answers are not merely ignored. Their amplitudes are rotated so they subtract. Right answers are arranged to add, so their probabilities grow when you finally measure. The computation is not the branching alone. The computation is the controlled recombination. This is why the word amplitude matters more than the word probability, even though probability is what you see on the screen. Probabilities only accumulate, and they behave like classical ignorance. Amplitudes can erase each other, and that erasure is the computational act, an operation on phase relations. It is also why small calibration errors can be fatal. because a tiny phase drift can turn cancellation into reinforcement. Visually, you can imagine a fan of translucent paths leaving a starting point, each path carrying a faint, oscillating glow. Some paths meet again, and where their crests align, the glow brightens. Where a crest meets a trough, the glow dims into nothing. The algorithm is the choreography that decides which meetings happen and with what phase. In a good algorithm, the choreography is robust enough that the brightening survives noise, at least long enough to be measured. Deutsch's earliest example was simple, but the logic scales in a way that is easy to miss if you only look at toy problems. You prepare a superposition over inputs. You apply a unitary that correlates inputs with outputs, often by entangling registers. You then apply another unitary that makes different histories interfere, converting hidden phase information into visible probability bias. In effect, the circuit turns a property of a function into a phase pattern, then turns the phase pattern into a measurement advantage. The key is that the intermediate histories are not directly observed, and that is not a philosophical footnote. They are still part of the evolving state, and they still affect the final statistics through constructive and destructive interference. If you measure too early, you collapse the pattern and lose the advantage. If you allow the environment to measure for you through stray photons or thermal vibrations, you lose it the same way. This is why quantum hardware is built around isolation and error correction, even when the algorithm itself is elegant. The computation is not only the gate list, it is the maintenance of coherence across many degrees of freedom while the gates act, and that maintenance is a physical struggle against the environment. The refrigerator is not just cooling, it is slowing the universe's habit of entangling your qubits with everything else. So the power question becomes sharper, and it stops sounding like a word game. If the algorithm's success depends on many paths existing long enough to interfere, what are those paths physically? Are they just counterfactual branches in our description, or are they real components of the world that persist until decoherence destroys their relationship? And if they are not real, why does engineering effort spent on preserving coherence pay off so predictably? In a classical circuit, a path is a metaphor for a sequence of bit updates, and the metaphor is safe because the machine is always in one definite state. Only one actual sequence occurs, because the hardware has a single configuration at each step. Even if you do parallel classical computing, each core still occupies one definite trajectory. The multiplicity is in the hardware count, not in the state of one core. In a quantum circuit, the state is not one basis state between gates, and that difference is not semantic. Between gates, the state is a superposition that includes many basis components at once. Those components evolve coherently under the same physical operation, and the final result depends on their relative phases, not just on their magnitudes. The machine is not trying options. It is evolving a single object whose internal geometry encodes those options. Entanglement makes this more than many independent qubits doing their own thing, because the state cannot be factored into separate pieces. The amplitudes describe correlations that have no classical analog, and those correlations are what let a small number of qubits represent a structured, global state. When engineers talk about depth and connectivity, they are talking about how quickly entanglement spreads. They are also talking about how quickly errors spread, because entanglement carries fragility along with power. At this point, you can feel the documentary's central tension tightening, because the mathematics insists on an exponential description. Yet the device looks stubbornly finite, like any other piece of electronics. The question becomes, is the exponential structure merely a convenient language, or is it the real arena in which the computation happens? If it is real, then the lab bench is touching something larger than the bench. Deutsch argued that the simplest mechanism is literal parallelism in the ontology, and he was explicit about what simplest means. The wave function describes what exists, not just what we know. The different terms in the superposition correspond to different real branches, each with its own version of the computation unfolding. The simplicity is that you do not add extra rules beyond unitary evolution. You just take it seriously. In that picture, a quantum computer is not a single computation with some mysterious shortcut. It is a coordinated family of computations occurring in parallel branches, all linked by a shared unitary evolution. The device's gates act across the entire branching structure, because the wave function is the object being manipulated. The algorithm is then a recipe for arranging how branches diverge and recombine, so that most branches cancel out of the final statistics. Interference then becomes cross-branch coordination, not a trick of ignorance or a bookkeeping accident. Branches diverge when information becomes effectively irreversible, which is what decoherence accomplishes in practice. Branches can also recombine when coherence is preserved and phases align. And that recombination is what an algorithm exploits. In this view, the refrigerator is not merely protecting qubits. It is protecting the possibility of recombination. This is the wager in Deutsch's title, even when it is not stated as a bet, because it forces you to choose where to put the explanatory weight. Either you accept many worlds as the mechanism behind the exponential state space, or you accept that the quantum speedup arrives by something like a miracle, meaning an unexplained causal gap between the hardware and the output distribution. The dilemma is not about comfort. It is about whether the computation has a place to happen. Deutsch did not mean miracle as an insult, and he did not mean that quantum theory is irrational. He meant that if the wave function is only a tool for predicting outcomes, then what physical process produces the outcome statistics so efficiently? What is it in the world that keeps track of phase relations across an exponential space while your refrigerator hums? What carries the phase, and where does it live, if not in something like the wave function itself? One alternative is to treat the wave function as epistemic, like a probability distribution over hidden facts, and this view has an intuitive appeal. Then the amplitudes do not correspond to real branches. They correspond to our uncertainty about a single underlying state, like a classical mixture we do not fully know. But the quantum computer does not behave like a system with mere ignorance. It behaves like a system with coherent phase relations that can be rotated and exploited. Deutsch's objection is that epistemic stories still owe you a mechanism for interference, because interference is not a feature of ignorance. If there is only one real history, then what is interfering with what? What carries phase information? And how does that phase guide the computation toward the right answer without being physically instantiated? If the phase is only in our heads, why does it respond to microwave pulses with such repeatable precision? Another alternative is to add hidden variables that pick a single outcome while preserving quantum predictions. And historically, this route has been attractive to people who want a single world. Then the wave function may be real or not, but the hidden variables do the selecting. The difficulty is that the selection must still reproduce the same interference-driven speedups without smuggling in non-local bookkeeping that is just as extravagant. The hidden layer must be rich enough to stand in for the exponential structure you tried to avoid. Even if you accept non-locality as a fact, the accounting problem remains, and it becomes sharper in a computational setting. The hidden variables must encode enough structure to mimic the effect of exponentially many amplitudes. If they do, you have not avoided the exponential arena. You have relocated it into a less transparent layer of theory, where it becomes harder to connect to engineering practice. Another alternative is objective collapse, where the wave function sometimes really collapses, and the collapse is a physical process. Then there is one world, and collapse is the mechanism that prevents macroscopic superpositions from persisting. The cost is that collapse must be tuned to avoid destroying the very coherence quantum computation needs, because quantum algorithms live in the delicate middle ground. If collapse is too eager, the algorithm dies. If it is too shy, the collapse story loses its motivation. Quantum computing does not merely tolerate that middle ground. It depends on it, because the algorithm's interference pattern requires coherent superpositions across many qubits for many gate layers. Collapse models must therefore draw a line between ordinary systems and too large systems, and the quantum computer tries to operate near that line without crossing it. That is an engineering constraint, but it is also an ontological pressure test. Every improvement in coherence time quietly tightens the test. Deutsch's argument presses on a common weakness across these moves. And the weakness is not that they cannot match the statistics. They can match the statistics on paper, and some are mathematically elegant. The weakness is that they often leave the computational work floating, as if the exponential structure is only in our equations, while the device somehow shortcuts the need for it. The question returns, stubbornly physical. What is the substrate that carries the phase relations the algorithm manipulates? Quantum algorithms behave as if the exponential structure is physically active, not merely descriptive. The machine's output distribution depends on phase relations among exponentially many components. If those components are not real, then the mechanism must still emulate their effects, and emulation is itself a kind of hidden resource. At some point, it's just math begins to sound like it happens by magic. This is where the documentary's tension shifts from interpretation wars to resource accounting, because accounting is where physics becomes concrete. In classical computing, you cannot get exponential advantage without exponential hardware or exponential time. And that is not a theorem of computer science alone. It is a reflection of how classical states compose and how classical information is stored. Classical correlations scale politely. Quantum correlations do not. In quantum computing, you seem to get exponential expressive capacity from linear hardware growth, and that is the unsettling asymmetry. Add 1 qubit and the Hilbert space doubles. Add 10 qubits and the space multiplies by 1,000. Add 50 and you are in a regime where classical simulation becomes a heroic approximation. The lab device is small, but the state it sustains is, in the formal sense, vast. The phrase exponentially large state space can mislead, so we pin it down with care. The system is not visiting 2 and classical configurations one by one, like an extremely fast classical computer. It is evolving one quantum state whose description requires 2 amplitudes in the standard basis. And the basis is a choice of coordinates. Change the basis and the list of amplitudes changes, but the underlying state and its capacity for interference does not. That description is not arbitrary, and it is not a matter of taste. It is the minimal structure that predicts all measurement outcomes after any sequence of gates. Because quantum theory is a theory of how those amplitudes transform. If you deny the reality of that structure, you must still explain why the device behaves as if it is there, and why interference works with such precision. Why does the same abstract vector picture keep paying rent in the laboratory? A useful way to feel the constraint is to imagine trying to classically track the state, step by step, as the circuit runs. Each gate mixes amplitudes, spreading information about phase across the vector. After enough entangling gates, the state becomes highly non-separable, and the classical description becomes a dense object. The quantum device does not store that object like a file. It embodies it as a physical state, and it updates it by letting the system evolve under carefully shaped electromagnetic pulses. Deutsch's many worlds mechanism offers a clean answer, and clean here means it does not add extra moving parts beyond the wave function itself. The amplitudes are weights on real branches. The computation is distributed across those branches. The final measurement is the observer finding themselves in one branch with a high weight outcome, because those branches were engineered to carry the surviving amplitude. The algorithm is then a kind of selective breeding of branches, performed by interference. The horrible implication begins to take shape here, because it is not about science fiction travel or portals. It is about what counts as the physical world, and whether space-time is the whole stage. If the wave function is real, then our lab device is operating on a structure larger than space-time, or at least not confined to the space-time picture we instinctively use. The familiar three dimensions become an interface, not the full accounting sheet. The chip on the bench becomes a cross-branch coordination machine, and that phrase is meant to feel both technical and uncanny. Its gates are not merely local switches. They are operations on a global quantum state that includes many mutually inaccessible histories, all evolving under the same unitary rule until decoherence makes them effectively independent. The machine's power is then the power to keep those histories mutually relevant. Visually, you can return to the refrigerator, but now the camera lingers on the cables and the shielding, as if they are ritual objects. Every attenuator and filter becomes part of a bigger purpose, keeping the branches coherent long enough to interfere. The laboratory becomes a place where the environment is carefully silenced, so that the wave function can remain a single, extended object. Even the quiet becomes a resource, purchased with engineering, patience, and cold. That makes the 200-second anomaly from Chapter 1 feel less like a performance trick and more like a clue. It becomes a hint that the universe's fundamental bookkeeping is not confined to the single narrative we experience. The extra reality is not created by the machine. It is recruited by preserving coherence, the way a lens recruits light that was already there. The device does not invent the arena. It holds the door open. This also reframes the central question of the series, and it raises a provocative possibility without leaving the topic at hand. If quantum speedup is best explained by many worlds physics, then reality is made of branching information structure. Civilizations that learn to engineer that structure might treat space-time as a surface layer, a convenient interface rather than the deepest substrate. The unsettling thought is that our everyday world may be the compressed summary of a much larger computation. In that future, the incentive is not only faster factoring or better chemistry, even though those are profound. The incentive is access to the deeper substrate where computation naturally lives, because that substrate would be where the exponential accounting is native. Leaving the physical cosmos behind would not mean escaping physics. It would mean moving deeper into the part of physics that does the counting, and it would raise a question we rarely ask. What does location mean if the arena is not space-time? Yet Deutsch's wager is not universally accepted, and we will not pretend it is settled by one argument. Many physicists use the formalism without committing to many worlds, and they do so successfully in their daily work. Yet the wager forces a disciplined question, and it is a question that quantum engineers cannot avoid forever. If you reject branching as real, what mechanism replaces it without adding unexplained machinery? What physical story makes the refrigerator, the pulses, and the interference fit together? Notice how the question is framed, because it is not a demand for metaphysical comfort. It is a demand for causal clarity, the same kind of clarity we expect from any other machine. When a jet engine produces thrust, we can trace the mechanism. When a transistor switches, we can trace the mechanism. When a quantum computer produces a distribution that resists classical simulation, we should be able to say what did the work. We should be able to point, not to a metaphor, but to a process. So Chapter 2 ends with a sharpened dilemma, not a conclusion, and the dilemma is meant to stay sharp. Quantum computation looks like a physical process that exploits an exponential structure. Either that structure is ontologically real, or our single-world story is missing a causal layer, a layer that becomes visible only when we force quantum coherence to do something useful. The machine becomes a test of interpretation, not by argument, but by performance. Deutsch did not invent this dilemma from nothing, and he did not conjure many worlds just to win an argument. He inherited it from a deeper dispute about what the wave function means, and that dispute predates quantum computing by decades. It was laid down in 1957 by a graduate student whose idea was treated as an embarrassment, partly because it sounded too literal and too vast. The physics community was willing to use the equations, but not to live inside their implications. Deutsch's claim didn't emerge from nowhere. It sits on a foundation laid by a dismissed graduate student in 1957. Next, we go back to Hugh Everett and the first attempt to take the wave function literally. We follow how a dismissed thesis became the only mechanism some quantum engineers can live with. Deutsch's wager points backward to a quieter origin story, written in 1957 and mostly ignored. It begins with a graduate student who refused to add a miracle, even when the miracle had become standard operating procedure. Hugh Everett III arrives at Princeton with a mathematician's temperament and a strategist's patience, and he steps into a department still glowing from the post-war boom. In archival photos, he looks almost anonymous. Dark suit, careful posture, an expression that suggests he is already running the argument ahead. He is not trying to shock anyone with metaphysics, and he is not looking for a poetic interpretation. He is trying to make the equations stop contradicting the story physicists tell themselves in lectures. The contradiction has a name that sounds technical, yet it is a plain human confusion. Quantum systems follow Schrödinger's equation, and that evolution is smooth, linear, and deterministic in the specific sense physicists mean. If you know the wave function now, the equation tells you the wave function later, with no gaps and no jumps. Linearity matters because it preserves superpositions, letting amplitudes add like overlapping ripples in a pond. But measurements appear to produce one definite outcome, with probabilities that look fundamental rather than merely practical. In the textbook, the wave function evolves like a wave until someone looks. Then it collapses into a single result, and the wave becomes a fact, as if nature suddenly changes its rules mid-sentence. The problem is that the theory never says what counts as looking, or what physical event flips the switch. Is it the click of a detector, the trace on a photographic plate, the ink in a notebook, or the awareness in a mind? A detector is made of atoms that should also obey Schrödinger evolution, and so is the electromagnetic field that couples it to the particle. A lab notebook is made of atoms that should also obey Schrödinger evolution, as are the photons that illuminate it and the retinas that read it. If everything is quantum, then the measuring device should become a superposition too, and so should the record. The discomfort is not mystical, it is mechanical. Physics seems to require a special exception for the very act of doing physics. So the measurement problem is not a séance, it is bookkeeping. We have one rule for isolated systems and a second rule for measurements, and the boundary between them is never written into the math. The second rule is collapse, and it is an extra postulate that arrives like a footnote. It is also an unusually powerful footnote because it changes a spread of possibilities into a single, public world. Collapse is also strangely selective, and that selectivity is part of what makes it feel ad hoc. It is not triggered by size alone, because small systems can decohere quickly and large systems can remain coherent in special conditions. Superconducting circuits can behave as single quantum objects, while a dust grain in sunlight is effectively classical almost instantly. It is not triggered by consciousness in any operational way, because experiments do not need minds to run, and automated apparatus can produce the same statistics. The vagueness is the point of pain. Collapse is invoked exactly where the theory stops being explicit. The Copenhagen tradition responds with a kind of disciplined refusal, and it is easy to underestimate how deliberate that refusal was. It treats the wave function as a tool for predicting outcomes, not a literal object floating in space. It says the job of physics is to calculate what we will observe, not to describe what exists between observations. In that view, asking what the wave function really is can sound like asking where the average lives. That stance works, and it built the 20th century. It helped turn quantum theory into transistors, lasers, magnetic resonance, and the precise timing that keeps satellites synchronized. Yet it leaves a gap that grows louder when we build machines that rely on unobserved quantum structure, and when we push experiments into regimes where measurement is engineered rather than assumed. It also leaves a young Everett staring at a theory that seems to demand two incompatible stories, both of which claim to be fundamental. Everett's move is brutally simple, and that simplicity is why it still haunts the field. Keep Schrödinger evolution always, for every system, including the laboratory and the observer. Remove collapse entirely, not by replacing it with a new mechanism, but by refusing to insert it at all. If the equation is the law, then it does not pause for human convenience. In Everett's thesis, there is one universal wave function, evolving unitarily without exception. Unitary is a technical word with a plain meaning. The evolution preserves total probability and keeps the mathematics reversible in principle. It also means information is not destroyed by the dynamics, even when it becomes inaccessible to one subsystem. Measurement is not a special process that breaks the rules, and it is not a magic boundary where physics becomes philosophy. Measurement is an interaction that entangles the system with the apparatus and the observer, spreading correlations outward like dye in water. Write the measurement as physics, and the mystery changes shape. The electron does not pick a position and force the detector to agree, as if the world negotiates with the instrument. The electron and detector become correlated, producing a joint state with multiple consistent outcomes. The wave function does not become a single fact, it becomes a structured record of relationships. In that joint state, there is a branch where the pointer reads left. There is a branch where the pointer reads right, and the microscopic details of the detector match, that reading down to the arrangement of charges and phonons. The observer becomes part of the correlation, with a memory that matches the pointer, and with a brain state that says, sincerely, I saw left. Each record is internally coherent, and that coherence is the point. Everett calls this a relative state formulation, and the word relative matters more than it first appears. The observer's state is relative to the outcome recorded in that branch, and the apparatus state is relative to the system state. There is no single global fact that must be selected by collapse, because the theory already contains all the consistent facts as correlations. The universe does not choose one narrative. It contains a set of mutually consistent narratives that no longer share information. This is the first beat of the many worlds idea, even if the label comes later and arrives with baggage. All outcomes occur, but they do not remain mutually visible, and that invisibility is not a metaphysical curtain. The branches cease to interfere in practice, so each observer experiences one result, with no access to the alternatives that also exist in the wave function. The experience of uniqueness is real, but it is local. The probabilistic feel of quantum mechanics becomes a self-location problem, and the phrase sounds abstract until you picture it. Before measurement, the observer is correlated with multiple future records, like a book that has been printed with several endings on different pages. After measurement, each copy finds itself with one record and calls it the outcome, because that is the only record it contains. The uncertainty was never about what the universe will do, but about which record you will become. Everett's proposal solves the measurement problem by refusing to add a measurement postulate and by refusing to privilege observation as a special act. It keeps the dynamics uniform, and it treats observers as physical systems made of the same stuff as detectors and dust. It also demands that we accept something emotionally expensive, because it does not protect the everyday intuition that only one thing happens. The expense is not just many worlds as a headline, which is how the idea is often sold and mocked. The expense is that the wave function is not merely a catalogue of possibilities, like a menu of options waiting for reality to pick one. It is the complete physical description, and the classical world is an emergent perspective inside it. The solidity of the world becomes a feature of information flow, not a fundamental axiom. Everett submits this to John Wheeler, who sees the technical elegance and the political danger at the same time. Wheeler is a figure of mid-century physics, charismatic, well-connected, and intensely aware of what the community will tolerate. He tries to sell it carefully, hoping to avoid the word worlds, because he knows the word will trigger a reflexive rejection. He frames it as a conservative move, because it removes collapse rather than adding new forces, and because it keeps the core equation untouched. The establishment does not hear it as conservative, and the mismatch is almost tragic. They hear it as a metaphysical land grab, a claim that physics must now account for an uncountable multiplication of realities. They also hear it as a solution that produces no new laboratory predictions, which in a pragmatic era sounds like a confession. If it cannot be tested differently, why fight about it? In 1957, the culture of physics is shaped by war, engineering, and rapid success, and the mood is not patient with foundational doubt. The Manhattan Project has recently proven that abstract theory can become decisive hardware, and the Cold War is turning universities into pipelines for applied research. Copenhagen pragmatism fits that culture because it lets you compute without arguing, and it lets you build devices without pausing for ontology. Shut up and calculate becomes a survival strategy in a crowded field, and also a kind of professional etiquette. Everett is asking for the opposite, and he is asking it with a calmness that makes it harder to dismiss as mere provocation. He is asking what the calculation means, and he is asking it in a way that multiplies reality rather than shrinking it. Many physicists treat that as a category error or as a distraction from real work, because the work of the time is producing spectacular results. When the equations predict experiments perfectly, the temptation is to declare the story finished. There is also a technical weakness in the early presentation, and critics seize it because it is real. Everett does not yet have a clean account of why branches do not interfere, or why macroscopic superpositions do not remain visibly present. Without that account, the theory sounds like it predicts obvious, persistent superpositions of cats and people, like a nightmare that should be seen in the lab. If all outcomes exist, why do we never catch them overlapping in daily life? So the idea is dismissed as philosophy, and Everett feels the dismissal as personal even when it is framed as methodological. He is not a charismatic evangelist, and he does not enjoy academic trench warfare, where reputations are traded like currency. He leaves physics for defense work, where the rules are clearer and the rewards are immediate, and where the meaning of an equation is less contested. In that world, You are judged by whether the system functions, not by whether the universe is one or many. His life becomes a mirror of his theory's early fate, and the parallel is hard to ignore. The idea persists in the literature, cited and then ignored, like a footnote that refuses to disappear. Everett persists in the background, doing calculations for systems that must work, even when nobody agrees on meaning. The man and the interpretation both become a kind of shadow, present, useful, and rarely invited to the center. The many worlds interpretation becomes a ghost in the field, and ghosts have a particular role in scientific culture. It is present whenever someone worries about collapse, then it is pushed aside when the conversation turns back to predictions. It survives because it is hard to kill a theory that removes assumptions instead of adding them, and because it keeps returning to the same wound in the formalism. If collapse is not defined, then the ghost keeps tapping on the wall. The missing bridge arrives decades later, and it arrives from a different direction. It is not a new interpretation, and it is not a new postulate, and it does not require you to like the word world. It is a dynamical process called decoherence, developed through work by several researchers as quantum theory met the messy reality of environments. It explains, in physical terms, why certain superpositions become effectively unobservable. Decoherence begins with an unromantic fact about the universe, and the visuals here are almost mundane. Everything interacts with its environment through photons, air molecules, vibrations, and thermal noise, and these interactions never fully shut off. Even in a vacuum chamber, blackbody radiation and stray fields whisper information into surrounding degrees of freedom. Those interactions entangle the system with countless degrees of freedom, most of which we never track. When that entanglement spreads, phase relationships become inaccessible locally, and phase is where interference lives. Interference requires that the different components of a superposition maintain a precise relationship, like two ripples that must remain aligned to create a stable pattern. As the environment picks up which path information, those delicate relationships become scrambled across an astronomical number of microscopic variables. Interference between different components of the superposition becomes effectively suppressed, not by a collapse, but by dispersion of information. The system still evolves unitarily, because the total wave function of system plus environment is still following Schrödinger's equation. But the reduced state, the part you can describe when you ignore the environment, looks like a classical mixture, a probability distribution over outcomes. The mathematics here is not mystical. It is tracing out degrees of freedom, a standard operation that discards inaccessible correlations. What remains behaves like ignorance, even if the total state is perfectly definite. Decoherence does not choose an outcome, and it does not create collapse, and that distinction matters. It explains why outcomes behave as if they were chosen, because the alternatives stop being able to interfere and therefore stop producing observable contradictions. It turns quantum superpositions into effectively independent histories, each carrying its own stable records. The world looks classical, not because quantum theory fails, but because quantum information leaks. This is why splitting is a misleading metaphor, even though it is hard to resist in narration. There is no single dramatic moment when the universe cleaves into two copies with a cinematic sound effect. Branching is continuous, local, and driven by information that becomes irreversibly recorded, often in fractions of a microsecond. The process is more like a photograph developing than a mirror shattering. A better description is proliferation, not division, and the difference is subtle but important. As interactions record which path information into the environment, the joint wave function develops components that no longer overlap in any useful way. The separation is in information space, not in spatial distance, and that is why it feels uncanny. Two branches can occupy the same room, yet be unable to exchange a single meaningful bit. The branches are not separated by walls in space-time, and that is where the metaphor of parallel universes can mislead. They are separated by the practical impossibility of reversing the environmental record, because the environment has become a vast ledger. To make them interfere again, you would need to gather and phase align an astronomical number of scattered correlations, including the states of photons that have already flown into space. In principle, it is allowed, but in practice, it is beyond reach. Decoherence also clarifies what counts as a measurement, and it does so without mentioning minds. A measurement is any interaction that amplifies microscopic differences into stable, redundant records. And redundancy is the key word. When many fragments of the environment carry the same information, the record becomes robust against disturbance. The environment is a measuring device, and it measures constantly because it is always copying information outward. That reframes the original puzzle about the boundary, the so-called cut between quantum and classical. The boundary is not a line drawn by consciousness or by laboratory etiquette, and it is not a philosophical border patrol. The boundary is where information becomes effectively irreversible, because it is copied into too many degrees of freedom to be recollected. Classicality is what it feels like when the universe keeps receipts. With decoherence, Everett's picture becomes workable in ordinary language, and the ghost gains a body. The universal wave function evolves smoothly, and the world we experience is a branch stabilized by environmental monitoring. The everyday world is not the default state of matter. It is a special regime where interference is suppressed so efficiently that alternatives might as well not exist. Yet they remain in the full description, silent and structurally present. Probability remains a hard topic, and the documentary does not settle it here because the debate is still alive. Everett needs a story about why squared amplitudes behave like chances, and why rational agents should weight branches by the Born rule. Later work tries to derive the Born rule from decision theory or symmetry, and the arguments can feel like philosophy wearing mathematical clothing. The question lingers: if all outcomes occur, what does it mean to say one is likely? Yet decoherence changes the status of the interpretation, and it does so in a way that even skeptics must respect. It turns many worlds from a bare assertion into a framework with a mechanism for classical appearance, grounded in open system dynamics. It explains why we do not see interference between macroscopic alternatives, and why the world looks like it has a single history. The ghost is no longer only an idea, it is a consequence of how entanglement behaves. It also explains why the metaphor of parallel universes doing computations is both tempting and dangerous. The branches are not separate theatres where copies of you run in lockstep, each with its own independent stage. They are components of one state that become dynamically isolated by entanglement with the environment, and their isolation is approximate rather than absolute. The vivid language is useful, but it can smuggle in the wrong picture. So Everett's ghost returns with a new face, and the field slowly changes its posture. The physics community begins to treat the universal wave function as a serious option, not because it is comforting, but because it is economical. It keeps the core equation and explains the rest as emergence, which is a style of explanation physicists already trust. The cost is conceptual, but the bookkeeping becomes cleaner. Now the story loops back to the 200-second anomaly, and the loop tightens the tone. A quantum processor is engineered to resist decoherence just long enough to exploit interference, and that just long enough is the whole battle. It maintains cross-branch coherence that everyday life loses almost instantly, and it does so with hardware that looks like a shrine to fragility. In close-up, You see gold wires, microwave lines, and a refrigerator that descends like a metal stalactite into darkness. In ordinary environments, branching happens so fast that interference becomes unobservable in practice, and the timescales are brutally short. A warm object in air is bombarded by molecules and photons, and each collision is a tiny measurement that spreads information. Even a single scattered photon can carry away a telltale imprint of position, turning a superposition into a set of non-communicating alternatives. The phase coherence that would allow branches to recombine is shredded into the environment, and the world becomes effectively classical. We do not notice this because it is the condition of noticing anything at all. In a quantum chip, engineers fight that process with refrigeration, shielding, calibration, and error mitigation, and the visuals become almost surgical. The device sits near absolute zero because thermal agitation is a constant interrogator. Magnetic fields are tamed, vibrations are damped, and control pulses are shaped with obsessive precision. The lab is quiet in a particular way, quiet enough that the remaining noise has names, spectra, and budgets. They are not just reducing noise, they are delaying world separation. This makes the quantum computer a kind of controlled boundary experiment, even if it is marketed as a product. It creates a region where alternative histories remain mutually relevant because the environment is kept from learning too much. It then uses gates to steer their phases so they cancel or reinforce, like choreographing ripples before the pond freezes. The computation is not only about states, it is about relationships between states. If decoherence defines the boundary of worlds, then quantum engineering becomes world boundary engineering. The device is a temporary refusal of the universe's default behavior, and it is a refusal purchased with extreme isolation. It is a place where the branches are kept close enough to talk, exchanging interference patterns before the environment forces them apart. The machine is not merely fast, it is delicately unfinished. That is why the many worlds language keeps resurfacing in quantum computing discussions, even among people who dislike metaphysics. The hardware is built to preserve the very thing that makes branching meaningful, which is coherent superposition across alternatives. The speed-up looks like a resource drawn from coherence across possibilities, and it is natural to describe that resource as if many outcomes are being explored. The metaphor is not proof, but it is a clue about what must be protected. Everett's life adds a human shadow to that technical point, and the shadow deepens the mystery. He proposed a clean solution, watched it rejected, and left the field, as if the world he described had no room for him. Decades later, the missing mechanism arrives, and the idea becomes indispensable to how we explain what engineers are building. The ghost does not return to haunt, it returns to be useful. The documentary's central question sharpens again, because the stakes are no longer academic. If quantum computation's advantage is best explained by branching structure, then reality's substrate is not a single classical history. It is a quantum state whose stable experiences are carved out by information flow, and whose apparent definiteness is a local achievement. The world is not a given, it is an outcome of dynamics. So the horror is not that there are countless cinematic universes, each with a different plot twist. The horror is that what we call one world is an information condition maintained by decoherence, not a fundamental unit. The universe is not one story, it is a branching computation, and we are patterns that persist inside one strand. When you say this happened, you are reporting which record you inhabit. And once worlds are defined by information, the next step is unavoidable. We must ask whether information is merely recorded in reality, or whether information is what reality is made of. Is the wave function a description of matter, or is matter a stable way for information to behave? The question sounds philosophical, but it presses on the same equations that built the chip. That question is where Chapter 4 begins, because it points beyond interpretation into ontology. If the wave function is an information object, then physics may be a theory of computation first, with energy and matter as its stable currencies. If that is true, then advanced civilizations might not expand outward in space, but downward into the substrate that does the branching. The frontier would not be distance, it would be depth. We return to the opening hook with a new edge, and the visuals tighten to the humming refrigerator and the scrolling readouts. In 200 seconds, 53 fragile quantum parts produced a distribution that mocked classical simulation, and they did it by holding coherence together against a universe that wants to leak it away. If that performance depends on keeping branches coherent, then the extra reality did not come from nowhere. It was always there, waiting behind decoherence, and we have learned to hold it open briefly. Now we follow the implication to its next layer, where information stops being a description and starts being the thing described. The many-world story explains how quantum speedups can happen without visible machinery, and it does so with a kind of unsettling elegance. It does not yet explain what the machinery is ultimately made of, or what pays the bill when outcomes become definite. Even if you accept the branching picture, you still have to ask what stabilizes a branch as a lived, recordable fact. In 200 seconds, 53 fragile qubits produced a distribution classical computers could barely chase, even with clever approximations and massive parallelism. The result was not a single number, but a textured fingerprint of probabilities, a pattern whose fine structure depends on phase. If branches are real, then the computation rides on branching structure, amplitude spreading into alternatives that later recombine in phase. If branches are only a tool, then the mechanism still needs a substrate, something physical that can store distinctions without collapsing into noise. The lab footage looks almost anticlimactic at first, because the drama is hidden under layers of metal and vacuum. A gold-colored dilution refrigerator hangs like an inverted cathedral, layered plates descending into colder and colder darkness. Its polished shields catch the light in soft rings, like the inside of a bell turned upside down. Coaxial cables braid downward in tight bundles, carrying microwave pulses that are timed like percussion. Each line is a controlled pathway for electromagnetic energy, tuned so precisely that a few stray photons can matter. Somewhere near the bottom, behind shielding and filters, the qubits sit as tiny circuits on a chip, macroscopic objects engineered to behave like atoms. They are superconducting loops and junctions, patterned by lithography, then cooled until electrical resistance vanishes. At millikelvin temperatures, thermal agitation is suppressed, and quantum energy levels become resolvable. The hardware looks like ordinary engineering, yet its job is to protect phase, which is an exquisitely fragile kind of order. This is where the story stops being about worlds and becomes about information. Not information as a metaphor, and not information as a motivational poster, but information as a physical currency. A currency with prices, budgets, and hard limits. Limits that show up as heat, as entropy, and as the stubborn irreversibility of records. When we say, the machine computed, we are also saying, the machine managed the flow of distinguishability. John Archibald Wheeler's career begins in the most concrete physics imaginable, where the stakes are measured in kilotons and critical masses. He works on nuclear fission, chain reactions, and the wartime urgency of matter, when understanding neutrons is not academic. In that world, a reaction is not a diagram on paper. It is a cascade that either dies out or runs away, depending on geometry, timing, and the statistical luck of collisions. That early context matters, because it trained Wheeler to respect thresholds and feedback. A reactor is a lesson in amplification, where microscopic events become macroscopic consequences. It is also a lesson in irreversibility, because once energy is released as heat, you cannot simply unrelease it. Those instincts follow him, even when he later speaks in the language of space-time and quantum states. Archival photographs catch Wheeler in different lighting, and the change feels like a shift in the century's mood. In one era, he is young, sharp-eyed, standing near chalkboards dense with cross-sections and scattering angles. In another, he is older, almost theatrical, gesturing as if space itself can be shaped by a hand. The shift is real because he later helps shape general relativity's modern language, where geometry becomes dynamical and space-time is allowed to respond. General relativity is often introduced as poetry about curvature, yet Wheeler treats it like engineering. The equations do not merely describe a stage where matter moves. They say the stage has elasticity, and energy tells it how to bend. In Wheeler's vocabulary, geometrodynamics becomes a way to think. Not particles on a background, but a background that is itself a participant. In that view, geometry is not decoration, but a field with its own degrees of freedom. Curvature can propagate as gravitational waves, and horizons can behave like one-way membranes. Wheeler is drawn to any place where a boundary becomes physical, because boundaries are where accounting becomes sharp. You can almost see the later information questions taking shape inside the earlier gravitational ones. Wheeler trains students who define the century, and he keeps returning to foundations because the foundations keep refusing to settle. He moves between the biggest scales and the smallest scales, looking for one rule that does not blink. He sees quantum theory and gravity as two dialects describing one underlying account, and he suspects the translation is not optional. The discomfort is not aesthetic, because mismatched rules imply mismatched ledgers. Everett's thesis passes through Wheeler's hands, and Wheeler feels the danger in a way that is both scientific and social. He wants the equations taken literally, because he distrusts vague exceptions. Yet he fears the cultural backlash, because splitting worlds sounds like metaphysics smuggled into physics. He also senses that the measurement problem is not a side puzzle. It is a sign that the notion of a thing is unstable. The measurement problem is easy to state and hard to live with, because it attacks the everyday idea of a single outcome. The Schrödinger equation evolves the wave functions smoothly, spreading amplitudes across possibilities. A measurement, as usually described, produces one outcome with a definite value. Where exactly does the smooth evolution become a single fact, and what physical process marks the boundary? Across decades, Wheeler's suspicion condenses into a phrase that sounds like a slogan, which is part of why it is remembered. He calls it from bit, and he means it as a unifying hunch rather than a finished doctrine. Physical it, the thing you point at, the detector event, the particle track, arises from informational distinctions that can be registered. The phrase is compact, but the claim is demanding, because it asks for a physics of registration. Wheeler does not mean that the universe is made of human language, or that reality waits for English nouns. He does not mean computer screens, code, or a cosmic spreadsheet. He means that at the bottom, physics is about answers to yes or no questions, because experiments resolve alternatives. A particle here or there, a detector clicked or not, a correlation present or absent. Pause on that word. Question. In physics, a question is not a conversation, and it is not a subjective act of curiosity. It is an interaction that forces a system into a set of mutually exclusive outcomes that can be told apart later. The apparatus is a filter that sorts possibilities into bins, and the bins are the beginnings of bits. What matters is not what we feel, but what the world can reliably distinguish. Information, in this operational sense, is not a vibe or a platitude. It is the count of distinguishable states a system can reliably occupy under real noise and real perturbations. It is also the structure of correlations between systems, which determines what can be known, predicted, and verified. Correlation is the quiet engine here. Without it, a record is just a fleeting fluctuation. A bit is not an abstract 0 or 1 floating in mathematics. A bit is a physical distinction that can be recorded and later checked, which means it must be encoded in matter or fields. It requires stability against noise, and it requires a mechanism that makes alternatives mutually exclusive in practice. A scratch on a disk, a charge on a capacitor, a magnetization direction in a domain. Each is a small physical asymmetry that can persist. That persistence is already a clue about cost, because stability is never passive in a warm universe. To keep a bit stable, you often need an energy barrier that suppresses random flips. Thermal agitation is always trying to blur your distinction, and engineering is the art of building walls high enough. If the wall is too low, the bit leaks away. If the wall is too high, switching becomes expensive. Quantum theory complicates this because the state is not a single alternative, at least not before measurement. Before any readout, the wave function encodes many possibilities with phase relations, and those phases are not decorative. They are the bookkeeping that allows interference, the cancellation and reinforcement that makes quantum algorithms special. Phase is the difference between a mere mixture and a coherent superposition, and the device lives or dies by that difference. Measurement produces one outcome, and that outcome is a bit carved out of a larger space. The carving is not free, and it is not only epistemic, as if it were merely about our ignorance. To get a stable outcome, the world must create a record that resists reversal. And resisting reversal is a thermodynamic statement. A fact is not just selected, it is stabilized. Decoherence spreads witch path information into the environment, and the record becomes effectively permanent. The environment is not a mystical sink. It is photons scattering, phonons vibrating, stray electromagnetic modes picking up traces. Each interaction entangles the system with more degrees of freedom, and the phase relationships become inaccessible. In principle, the evolution remains unitary, yet in practice, the relevant interference is gone. A useful way to picture decoherence is to imagine ink dropped into water, not because quantum states literally dissolve, but because information disperses. The ink molecules still exist, and the water still obeys reversible laws in principle. Yet recovering the original drop requires controlling an astronomical number of microscopic details. For all practical purposes, the record is written. So the classical world is not simply the world of big objects. It is the world of irreversible records, where information has been copied outward into many redundant places. A fact is what remains after correlations have been amplified and stabilized, after the environment has become an unwitting archive. The now becomes history when it becomes hard to uncopy. Wheeler's it from bit is often misheard as idealism, as if mind creates matter by attention. Wheeler's intent is sharper and colder, and it is aimed at physics, not psychology. He is asking whether physics is fundamentally a theory of information processing, where processing means lawful transformation of distinguishable states. If the distinctions cannot, even in principle, be registered, then what are we claiming exists? If that is true, then computation is not a metaphor we impose on nature after the fact. Computation is what physical systems do when they evolve from state to state under constraints. The universe is not like a computer in the casual sense. It may be a computer in the strict physical sense, where dynamics is the hardware. The metaphor becomes a measurement program because it demands an energy and entropy balance sheet. That claim needs grounding because philosophy alone cannot carry the weight of a scientific program. The grounding arrives through thermodynamics, where information meets heat. The key figure is Rolf Landauer at IBM, looking at logic through the lens of physics and refusing to let bits float free of atoms. He treats computation as a physical process that must obey the same laws as engines and refrigerators. Landauer works in an era when computation is becoming an industrial force, not just a mathematical curiosity. Rooms of equipment shrink into cabinets, then into chips, and the switching speeds climb. Engineers see heat as an obstacle, something to be removed with fans and heat sinks. Landauer asks a deeper question. Is heat merely an engineering nuisance, or is it part of the definition of computation? In other words, is there a minimum heat you must pay to make a logical operation real? Landauer's principle begins with a simple question about erasing a bit. Not flipping a bit and not moving a bit, but erasing it, which sounds innocent until you define it carefully. Erasure means forcing many possible states into one standard state, so that the device is ready for reuse. It is the act of making a memory blank in a way that is reliable, not merely hopeful. In a memory element, unknown can mean either 0 or 1, and both are allowed. Erasure takes that set of possibilities and compresses it into a single outcome, like always resetting to 0. That many-to-one mapping is logically irreversible, because you cannot reconstruct the input. If both 0 and 1 become 0, then the past is lost in the output. Logical irreversibility, Landauer argues, has a physical cost, because losing distinctions is not abstract. When you discard information about microstates, you increase entropy somewhere else. The missing detail does not vanish. It is pushed into degrees of freedom you no longer control, typically as heat. The world keeps the information, but it moves it into places you have agreed not to track. At temperature T, erasing 1 bit dissipates at least kT ln2 of heat. K is Boltzmann's constant, and ln2 is the price of compressing 2 possibilities into 1. The bound is small per operation, but it is not negotiable. It is a floor set by the statistical structure of thermal physics. Lower the temperature and the floor drops, which is why cooling is not just convenience. It is strategy. To make the bound feel less like a magic number, think in terms of probabilities. A memory with 2 equally likely states has an entropy of k ln2. Erasure reduces that entropy in the memory because it forces the state into a known value. The second law demands compensation, so the environment must gain at least that much entropy. Heat is the usual currency for that gain. Landauer's point is not that today's computers already run at that limit, because most devices are nowhere close. Real transistors waste far more energy than the bound, because engineering is messy and because speed demands strong driving. His point is that the limit exists because information is physical and physics keeps accounts. Even an idealized device cannot escape the bookkeeping if it performs irreversible logic. This is the bridge Wheeler needed, because it turns it from bit into an accounting rule rather than a slogan. If information is real, then it must obey conservation-like constraints, even if the conserved quantity is not a simple number. The universe cannot compute without paying, because erasure produces heat, and heat is entropy carried into the surroundings. The phrase starts to sound less mystical and more like a ledger entry. The key is understanding what counts as erasure in the real world, because devices do not come labeled with philosophical categories. Anytime a physical process compresses phase space, it discards distinctions. Anytime a device resets memory, It pushes microscopic details into uncontrolled degrees of freedom. The trash is not thrown away. It is thermalized. A classical logic gate can be implemented reversibly in principle, and this matters for the story's tension. Gates like AND and OR are logically irreversible because they map multiple inputs to one output. Yet you can build reversible gates like the Toffoli gate that preserve enough information to allow inversion. If you avoid many-to-one operations, you can avoid the Landauer cost locally. But a useful computer must eventually discard information somewhere, if it is to produce a clean output and remain usable. You can keep garbage bits around, but storage is finite and correlations accumulate. At some point you reset memory, or you overwrite, or you compress. The entropy bill appears at the edges and sometimes inside, depending on the architecture. A computation that never discards anything becomes a computation that drowns in its own clutter. Even if the core computation is reversible, the input must be prepared, and the output must be recorded. Preparation and recording involve resetting degrees of freedom into standard states, which is a form of erasure. The world cannot hand you a pristine register for free. Someone, somewhere, must cool it, stabilize it, and push entropy out, so thinking generates heat, not as a poetic claim, but as a thermodynamic necessity. Every time a system erases correlations it once had, it must dump entropy. Computation requires physical irreversibility somewhere in the total process, even if parts of the evolution are reversible, like idealized mechanics. The irreversibility can be hidden, delayed, or exported, but it can't be abolished. We can see this in the most mundane places, because the universe leaves receipts in the form of warm metal and spinning fans. CPUs heat up when they switch, because real transistors are lossy, and because interconnects have resistance. Memory is constantly refreshed, because charge leaks, and because error rates rise with temperature. The sleek laptop becomes a small heater on your desk, and that is not an accident. Data centers make the point impossible to ignore. Rows of racks stretch into the distance under harsh white lighting, and the air itself becomes part of the machine. Cold aisles and hot aisles channel flow like engineered weather. The cloud is not weightless. It is a thermodynamic machine that moves energy, pumps heat, and consumes infrastructure. The numbers scale from the microscopic to the planetary, and the scaling is the story. Billions of operations per second become megawatts of power and rivers of waste heat. Cooling towers vent warmth into the sky, and backup generators wait like silent animals. The digital world has a climate footprint because computation is physical work done against noise. When we say information age, we are also describing an age of managed entropy. Brains are not exempt, even if their architecture is different and their goals are not arithmetic. Neurons fire, ion gradients reset, neurotransmitters recycle, and metabolic energy becomes heat. The brain runs on electrochemical potentials maintained by molecular pumps. Those pumps restore order locally by exporting entropy, and the body carries the cost away in warm blood. Thermal cameras make this visible in a quiet way. A forehead glows slightly warmer after effort, and a handprint lingers on a table. The heat is small, but the principle is the same. A mind is a computation embedded in chemistry, and chemistry must pay Landauer somewhere, even if the accounting is distributed across many processes. The bill is paid in glucose and oxygen, then written out as warmth. This is not a reduction of thought to mere heat, and it is not a dismissal of meaning or experience. It is a constraint on any physical implementation of memory and decision, whether silicon or neurons. If a system makes stable distinctions, it must manage entropy, and managing entropy means exchanging energy with an environment. The mystery remains, but it is now constrained by physics. Now return to quantum measurement, because measurement is where bits are minted. A measurement outcome is a record stored in a macroscopic apparatus and its environment, not just a number in an observer's head. That record is created by amplification and by irreversible coupling to many degrees of freedom. The pointer moves, the voltage spikes, the detector avalanche spreads. In the lab, readout often looks like a pulse and a trace on a screen. Underneath, it is an engineered instability. A tiny quantum difference nudges a system into one of two macroscopic basins of attraction. Once the avalanche starts, it recruits countless electrons, phonons, and photons, and the environment learns the answer. The apparatus does not merely observe, it commits. Decoherence explains why branches stop interfering, but Landauer explains why records become costly. Recording is not just entanglement, it is entanglement plus irreversibility, and irreversibility has a thermodynamic signature. The classical world is the world where information has been paid for in heat, because stable records require entropy export. A robust fact is a cooled, amplified, and redundantly copied correlation. This reframes the measurement problem as an information economy problem, which is both clarifying and unsettling. The universe does not hand out definite facts for free. Definite facts are stabilized by thermodynamic processes that dump entropy into the environment, and the environment becomes the ledger that prevents reversal. If you want a world with durable outcomes, you are also asking for a world that runs an entropy budget. A quantum computer lives in tension with this economy, and that tension is visible in its hardware. It needs coherence, which means it must avoid uncontrolled information leakage into the environment. Yet it also needs readout, which means it must create irreversible records at the end, because an answer that cannot be recorded is not an answer you can use. Even error correction is part of the bargain, because it fights noise by spending resources. So the quantum advantage is not only about many branches or many amplitudes. It is also about delaying the moment when information becomes classical, delaying the moment when the environment collects its copy. The refrigerator and shielding are not only protecting phases, they are postponing thermodynamic bookkeeping, keeping the system from paying too early. The computation is a careful deferral of irreversibility. This is why the opening hook feels different in this chapter. The 200-second miracle is not just a victory over classical simulation or a headline about supremacy. It is a controlled negotiation with the cost of information, where coherence is preserved and erasure is managed. The machine is not only computing, it is budgeting entropy. If information has a thermodynamic price, then reality is not free to compute arbitrarily. There are limits to how much can be known, stored, and erased per unit energy and per unit time. Those limits are not merely practical. They are written into the second law, and they make the laws of physics look like rules of an information economy. The universe can be lavish with possibilities, yet strict with records. That economy has a strange feature. You can shuffle information around almost for free if you do it reversibly. You can also hide information in correlations, which quantum systems do naturally. But when you demand a clean, standardized memory state, you are asking for compression. Compression is where the bill comes due, because you are throwing away alternatives. Wheeler's arc then reads like a long attempt to unify these constraints across domains that seem unrelated. General relativity teaches that geometry responds to energy and momentum, and that horizons behave like one-way surfaces. Quantum theory teaches that outcomes are tied to information and measurement, and that evolution is unitary in closed systems. Wheeler suspects the missing link is that space-time itself might be an informational construct, shaped by what can be distinguished. The suspicion gains teeth when we look at the most extreme thermodynamic objects. where gravity and heat become inseparable. Black holes are not just gravitational traps. They are information puzzles with a surface you cannot look past. They swallow matter, radiate heat, and seem to threaten the bookkeeping of quantum theory. They force the question, what counts as a record when the recorder disappears behind a horizon? A black hole has entropy proportional to its horizon area, not its volume, and that is a clue with sharp edges. In ordinary matter, entropy scales with the number of microscopic constituents, which scales with volume. In a black hole, the scaling suggests that information storage in gravity is strange. It suggests that space-time might encode information on boundaries, as if reality is compressed onto surfaces. Visually, the horizon is almost too clean. It is a dark sphere against star fields, a perfect absence that still has temperature. The idea that a black hole is hot, radiating faintly like a coal, sounds contradictory until you follow the quantum field theory. Hawking's calculation shows that horizons are not passive. They create radiation because vacuum fluctuations are distorted by gravity. Hawking radiation raises the sharpest version of the question. If black holes evaporate, what happens to the information about what fell in, the detailed correlations that defined the initial state? If information is lost, quantum mechanics breaks its own rule about unitary evolution. If information is not lost, then it must be encoded somehow in the radiation, in correlations so subtle that they look like noise. The paradox is an argument about bookkeeping, not about romance. So the black hole becomes the ultimate audit of it from bit. Gravity, thermodynamics, and quantum theory collide in one object, and none of them can be ignored. If the universe is an information process, black holes are where the process is most constrained, because horizons behave like accounting boundaries. They force you to say where the bits are and who can access them. This is why Wheeler's phrase survives, despite sounding like a bumper sticker when stripped of context. It points to a program rather than a conclusion, and programs can survive uncertainty. Find the informational substrate that makes both quantum measurement and space-time geometry make sense. Find the rule that tells you why a record is stable and why a horizon has entropy. Landauer's principle keeps the program honest because it forbids hand-waving about infinite computation. You cannot claim infinite computation without infinite heat disposal, because erasure piles up entropy. You cannot claim perfect records without paying entropy somewhere, because perfect stability requires isolation or redundancy. The universe does not allow a free lunch, even in principle. The implication is unsettling in the context of the series' central question. If quantum speedup is real, then the universe supports computation beyond classical accounting, at least beyond naive classical simulation. If information is physical, then that computation is constrained by thermodynamic costs, and those costs shape what is feasible. The question becomes not only what can be computed, but what can be computed without drowning in entropy. So what would an advanced civilization optimize if it understood this substrate and treated it as engineering rather than philosophy? It might not chase raw energy alone, or raw matter alone, because energy without a cold sink is trapped. It might chase low entropy resources, cold reservoirs, and architectures that minimize erasure. It might value temperature gradients the way we value fuel. It might also chase reversible computation, not as a niche trick, but as a survival strategy. If erasure is expensive, then the future belongs to systems that keep information coherent and avoid discarding it. The deepest form of efficiency is not faster clocks. It is fewer irreversible steps, fewer moments where possibilities are crushed into one. That idea loops back to many worlds in a new way, and the loop is tight. Branching is what happens when information leaks and records become irreversible, because the environment locks in alternatives. A civilization that can control leakage can control branching, at least locally. It can decide when a system must pay the cost of becoming classical. Now the horror shifts from multiplicity to economics. The universe is not an infinite free playground of computations, where you can explore every possibility at no cost. It is a constrained ledger where every stable bit has a heat shadow, and every clean reset leaves a warm trace. The shadow is not moral, it is physical. Even our sense of a single classical history becomes a thermodynamic artifact, which is a strange thought to sit with. We remember one outcome because the environment has paid to make that outcome redundant, copied into many places. The past is the set of records that were expensive enough to persist, and forgetting is what happens when records are allowed to dissolve. In that sense, memory is a kind of cooled-down correlation. This also suggests a new way to interpret the quantum computer's strange power. The device is not merely sampling from a distribution as if it were a fancy random number generator. It is temporarily maintaining an informational structure that the warm universe usually destroys, preserving phase relations that would normally be taxed away by decoherence. The surprise is not that it computes, but that it holds the line against thermalization. The machine is a small region where the information economy is bent, because the environment is kept from collecting its usual taxes. Coherence is a kind of credit, and decoherence is the interest coming due. The longer you hold coherence, the more carefully you must isolate, cool, and correct. The bill is delayed, not erased. If that is the substrate, then space-time itself may be downstream of information constraints, which is Wheeler's deeper temptation. Geometry could be the large-scale bookkeeping of correlations, the way a thermodynamic variable summarizes countless microstates. Gravity could be the macroscopic behavior of information under compression, the way pressure emerges from molecular motion. The analogy is not proof, but it is a direction. We are not proving that here, and we are not claiming the final theory is already in hand. We are setting the direction with the tools we have earned. Wheeler's journey points from particles to geometry to measurement to information, and Landauer's bound tells us the journey has a price tag. The price tag is what makes the story scientific, because it can be checked. Now we need the modern synthesis that makes the hint concrete, and modern physics has been inching toward it. In recent work, entanglement stops being a curiosity and becomes a building material, because it is the structure that defines what is correlated with what. Space-time geometry begins to look like a pattern of quantum correlations, a kind of emergent order. The question becomes practical. What does it cost to maintain that pattern against decoherence? The story now turns to a startling modern synthesis. Entanglement may stitch space together, and wormholes may be another name for quantum links. If it from bit is right, then the next chapter asks what space is made of when the bits are entangled, and what the universe is paying when it keeps them that way. Chapter 4 ended with a wager about substance, because we kept circling the same stubborn claim. If information is physical, then space might be accounting, an inventory system that tracks what can happen and what cannot. Black holes force that accounting into public view, because they turn gravity into a thermodynamic object with measurable bookkeeping. In the early 1970s, Jacob Bekenstein argues that a black hole must have entropy. Otherwise, the second law fails in an almost embarrassing way. Picture a cup of hot tea, glowing faintly in infrared, falling toward a dark horizon. The tea carries entropy, which is just a count of microscopic arrangements consistent with what we see. If the tea disappears, and the black hole has no entropy, then total entropy drops. That would make the second law optional, depending on whether gravity is present. Bekenstein's move is to say that the black hole itself must gain entropy when it swallows matter. The horizon becomes a place where missing information is tallied. This is not a poetic flourish, because Bekenstein proposes a bound on information storage. The maximum entropy inside a region cannot exceed a value proportional to its boundary area. The suggestion is radical, yet it is anchored in thermodynamics. Nature dislikes violations of the second law. Then Stephen Hawking pushes the argument into a calculation that cannot be ignored. In 1974, using quantum field theory on curved spacetime, Hawking finds that black holes are not perfectly black. They radiate like hot objects. The visual is stark if we slow it down. Near the horizon, quantum fluctuations constantly produce pairs of particles and antiparticles. Most pairs annihilate quickly, returning their borrowed energy to the vacuum. But gravity can separate them, so that one falls inward while the other escapes to infinity. To an outside observer, the escaping particle looks like radiation emitted by the black hole. The black hole loses mass, as if it is cooling by shining. Once a black hole has a temperature, it must have a thermodynamic entropy. Temperature and entropy are linked by the laws of thermodynamics, and Hawking's result makes the linkage unavoidable. The entropy can't be metaphor, because the radiation is real. The shock is the scaling, and it remains shocking even after decades of repetition. Black hole entropy grows with horizon area, not with interior volume. For ordinary matter, entropy is extensive, meaning it scales with volume. A gas in a box has more possible microstates when the box is larger. A black hole behaves differently, as if the interior is not where the degrees of freedom live. The entropy is proportional to the area of the event horizon, measured in Planck units. Those Planck units matter because they hide the constants that set the quantum gravity scale. The formula contains Newton's constant, the speed of light, Planck's constant, and Boltzmann's constant. It is a compact collision of gravity, quantum theory, and thermodynamics. If entropy counts microscopic possibilities, then the microscopic possibilities seem to live on a surface. The horizon behaves like a physical membrane that stores information. It is as if the universe keeps its deepest records on boundaries, not in volumes. That is the first hint of holography, and it lands like a change of perspective. A three-dimensional region might be fully described by information on its boundary. The boundary description is not a compressed summary, but a complete alternative formulation. Use an intuitive picture, then strip it of comfort, because the intuition is both helpful and misleading. A 3D scene can appear on a 2D screen, and we accept the trick because we know the screen is an approximation. In holography, the boundary is not a projection that loses detail. Instead, the boundary is a ledger that is mathematically sufficient, with no missing entries. Every bulk event has a boundary encoding, even if the encoding looks nothing like the event. The surface does not display the world. It defines the world. On screen, show a rotating black hole silhouette, then overlay a thin glowing shell around it. Let the shell fill with shifting symbols, as if it is a living spreadsheet. The point is not that the horizon is literally a screen, but that it behaves like one in the accounting. This idea grows from black hole bookkeeping into a general principle, because the logic does not stay confined to collapsed stars. The maximum information in a region seems limited by area, as if nature caps storage by surfaces. Gravity looks like it enforces that cap, because horizons behave like physical boundaries. The historical context matters here, because the holographic principle did not appear from nowhere. Gerard 't Hooft and Leonard Susskind sharpened the idea in the 1990s, motivated by black hole entropy and the information paradox. They argue that a consistent quantum theory of gravity must be holographic in this sense. The information paradox is the pressure behind the story, even when we do not name it every time. Hawking radiation looks thermal, and thermal radiation seems to erase details. If a black hole evaporates completely, where does the information about what fell in go? Quantum mechanics insists on unitary evolution, meaning information is preserved in the full quantum state. Thermality suggests the opposite, because a thermal spectrum looks like a loss of memory. The paradox is not a philosophical itch, it is a clash between two pillars of physics. Holography offers a way to keep both pillars standing, because it changes where the information lives. If the boundary encodes everything, then evaporation can be unitary, even if the bulk description looks forgetful. The horizon becomes a regulator that prevents the bookkeeping from breaking. Now introduce the modern breakthrough that made holography concrete, because principles become useful when they become calculable. In 1997, Juan Maldacena proposes a precise duality, now called ADS-CFT. It states that two very different theories can be exactly equivalent. The visual should shift from the black hole to a clean geometric diagram. Show a cylinder-like space-time with a bright boundary wrapping around it, and a deeper interior labeled as the bulk. Let the camera drift from the boundary inward, then snap back outward as if the boundary has priority. One side is a gravity theory in a higher dimensional bulk space-time. The other side is a quantum field theory without gravity, living on the boundary of that space-time. The equivalence is not approximate, and it is not a metaphor. To physicists, this is a duality, meaning two descriptions of the same underlying physics. It is like having two languages that can express the same facts, even if the grammar is completely different. If you compute a quantity on one side, you can translate it to the other side. The conceptual leap is brutal because it denies our default hierarchy. A world with gravity and an extra spatial dimension can be rewritten as a world with no gravity and one fewer dimension. Space-time geometry becomes something that can emerge from non-gravitational quantum information. ADS is a special kind of space-time with negative curvature, and it provides a clean boundary at infinity. Negative curvature means geodesics diverge, and volumes grow faster than in flat space. The geometry feels like an infinite interior with a well-defined edge. CFT is a conformal field theory, a quantum theory with special symmetry that makes calculations tractable. Conformal symmetry means the theory looks the same under local rescalings of distance, so there is no preferred length scale. That symmetry is technical, yet it is also a clue. The clue is that scale becomes negotiable, and in holography scale is tied to depth in the bulk. Roughly speaking, moving inward in RDS corresponds to probing lower energy, longer distance features in the boundary theory. The extra dimension behaves like a scale dimension. The details matter to physicists, yet the message matters to everyone, because it changes what we mean by fundamental. If the duality is true, then the bulk is not fundamental. The boundary theory already contains the full content, including black holes and gravitational waves. Gravity becomes an emergent description of boundary degrees of freedom, like fluid dynamics emerging from molecules. A fluid has waves, vortices, and turbulence, and those are real at the right scale. Yet the fluid is not fundamental, because it is built from atoms. This reframes Wheeler's ET from bit in a sharper dialect. It is not only that physics uses information, but that geometry itself can be encoded as information. The stage is no longer assumed because the stage can be derived. A key point must land cleanly, because it is easy to lose the thread in the mathematics. In ADS-CFT, the boundary theory is ordinary quantum mechanics and quantum field theory, with unitary evolution and no space-time curvature. Yet the bulk description contains curved space-time, horizons, and gravitational dynamics. So where does the bulk come from, if the boundary already has everything? The answer that keeps returning is entanglement, because entanglement is the structure that ties quantum systems together. The pattern of quantum correlations in the boundary state determines the shape of the bulk geometry. Make the stitching idea accessible without turning it into fantasy, because the temptation is to anthropomorphize space. Distance is not a primitive number. It is a measure of how strongly systems can influence each other. If correlations are the only real links, then geometry is a map of those links. In ordinary life, we infer distance from travel time and effort, and we treat it as a background fact. In quantum theory, what is operationally meaningful is how one subsystem affects another through interactions. If interactions are constrained, then effective distance is large. Entanglement is a special kind of correlation that cannot be reduced to shared ignorance. It is a joint quantum state whose parts have no independent description. When entanglement changes, what is connected to what changes even if no signal is sent? That last clause matters because it protects causality while still allowing structure. Entanglement can be created by interactions, and it can be redistributed by unitary operations. Yet it cannot be used by itself to send a controllable message faster than light. In holographic models, entanglement entropy becomes a geometric quantity, and this is where the abstraction becomes a tool. The Ryu-Takayanagi relation ties entanglement on the boundary to the area of a minimal surface in the bulk. The equation is technical, yet the implication is simple. The minimal surface is like a soap film stretched across a wire frame, finding the smallest area consistent with its boundary. In the bulk, you pick a region on the boundary, then you look for the least area surface that anchors to its edge. The area of that surface computes the entanglement entropy, so areas in spacetime can be computed from entanglement in a non-gravitational theory. Geometry becomes a derived statistic of quantum information. The bulk looks smooth when entanglement is dense and structured, because smoothness is an emergent average over many correlations. This is not just a pretty correspondence, because it hints at a mechanism. If you change the entanglement pattern, you change the minimal surfaces, and the bulk geometry responds. The metric, which tells you distances and times, becomes a summary of correlation structure. Now push the idea into narrative tension, because the story is not only elegant. If entanglement is reduced, the bulk can pinch and disconnect. If entanglement is increased, the bulk can become more connected, as if space thickens where correlations are rich. Show this visually as a mesh that tightens and loosens. When correlations weaken, the mesh thins, and a neck forms like a stressed fabric. When correlations strengthen, the mesh fills in, and the geometry regains continuity. This is the chapter's escalation, and it should feel like the floor shifting under familiar concepts. Earlier we argued that information matters, because it has thermodynamic cost and controls branching. Now we argue that information builds space, because correlations define the very notion of adjacency. That sets up the next, stranger bridge, because general relativity already contains a hint of connectivity beyond ordinary intuition. In 1935, Einstein and Rosen find a mathematical connection between two regions of spacetime, now called an Einstein-Rosen bridge. In popular language, it becomes a wormhole. The original context is important because Einstein and Rosen were trying to understand particles as geometric objects. They explored whether a bridge could represent an electron without a singularity. The mathematics produced a connection, but it did not produce a usable tunnel. Wormholes are often sold as tunnels you can travel through, and the imagery is irresistible. In the classical solutions, the simplest bridges are not traversable because they collapse too quickly or require exotic conditions. The bridge exists as geometry, not as a highway. In a cinematic shot, you can show two distant regions of space connected by a throat of curved geometry. Then show the throat flicker and pinch shut before anything crosses. The lesson is that geometry can connect without permitting passage. Now introduce the conjecture that fuses the two stories, because it is a rare moment when separate puzzles rhyme. Maldacena and collaborators propose ER equals EPR. EPR refers to entangled pairs, named after Einstein, Podolsky, and Rosen. The EPR paper was itself a protest, because Einstein disliked the implications of quantum mechanics. He called entanglement spooky action at a distance, and he hoped it signaled an incompleteness. The irony is that the same initials now label a possible foundation for space-time connectivity. ER refers to Einstein-Rosen bridges. The conjecture says that entanglement and wormholes are two faces of one underlying structure. Maximally entangled systems may be connected by a non-traversable wormhole in an appropriate gravitational description. The cleanest thought experiment uses two black holes, prepared in a special entangled state. In the bulk description, they can be joined by a bridge, even if the black holes are far apart in ordinary space. The bridge is not a tunnel you can traverse, but it is a geometric representation of the entanglement. State what this does not mean, because the audience will immediately reach for science fiction. ER equals EPR does not allow faster-than-light messaging, because entanglement alone cannot transmit controllable information. The wormhole is non-traversable, and causality remains intact. Even if a bridge exists in the geometry, it does not open a loophole in relativity. To send a message, you need a signal you can modulate, and entanglement correlations can't be modulated into a message without a classical channel. The bridge is a correlation structure, not a communication line. State what it does mean, because the meaning is still unsettling. The geometry of connection and the quantum structure of correlation might be the same thing, written in two languages. A link in Hilbert space can be a bridge in space-time. This is where the documentary's tone should tighten, because the implication is not decorative. If wormholes are entanglement, then space-time connectivity is not a primitive fact. It is a consequence of how quantum degrees of freedom are paired and shared. The horror is subtle, and it is not science fiction, because it attacks the independence of inside. The inside of a region might not be an independent place, because the interior can be reconstructed from boundary information. Going inside might mean changing the description, not traveling through space. In holography, the boundary theory contains operators that can reconstruct bulk events. The interior is not hidden by distance, it is hidden by encoding. The map from boundary data to bulk geometry is complex, yet it is still a map. The encoding is not arbitrary, and it has structure that resembles error correction. In quantum error-correcting codes, information is stored non-locally, spread across many physical qubits. Losing a few qubits does not destroy the logical information, because the information is redundantly encoded. Holography suggests something similar about space-time, because bulk information can be recoverable from different boundary regions. That redundancy is not a minor technicality, because it changes what location means. A bulk event can have multiple boundary reconstructions, depending on what data you access. This reframes the meaning of locality, and it is a direct continuation of the earlier claim about adjacency. 2 points can be far in emergent space, yet close in the underlying quantum network. The geometry we trust might be a coarse-grained story that hides deeper adjacency. Show a network diagram that looks nothing like a map, with nodes connected by weighted edges. Then let that network slowly morph into a smooth surface, as if the surface is an averaged visualization. The viewer should feel that the smooth world is an interpretation. Now connect back to the earlier many worlds tension about probability and records, because the series has been building this pressure. If branches are defined by decoherence and information flow, then space-time itself may also be branch relative. Different coarse grainings can yield different effective geometries. Decoherence picks out stable records, and stable records define what counts as a classical history. If geometry is also an emergent record, then geometry inherits that conditionality. The same underlying quantum state can support multiple effective classical descriptions, each with its own space-time story. We do not resolve the born rule here, but we sharpen the discomfort, because the discomfort is part of the narrative engine. If reality is a universal wave function, then geometry is part of the wave function's emergent structure. Probability becomes a rule for navigating emergent descriptions, not a primitive cosmic dice. Now return to the quantum computer, because it is our experimental handle on these abstractions. A quantum processor is a controllable entanglement factory. Gates create, move, and reshape entanglement patterns across qubits. In the lab, you can watch this indirectly through interference patterns and measurement statistics. You cannot see entanglement with your eyes, but you can infer it from correlations that violate classical bounds. The processor becomes a microscope for Hilbert space structure. If entanglement is geometry, then quantum circuits are sculpting tiny abstract geometries in Hilbert space. The chip is not bending space-time in the lab, yet it is manipulating the same kind of structure that holography uses. It is building connectivity in the only place quantum theory guarantees, the state space. Visually, show a cold metal dilution refrigerator, cables descending like roots into darkness. Then transition to an animated lattice of qubits, where gates light up edges between nodes. Let the edges thicken where entanglement accumulates, as if a geometry is being woven. This makes the opening hook feel different again, because the earlier speedup now has a new interpretation. In 200 seconds, the processor explored a state space too large for classical bookkeeping. If that state space is the substrate, then the computation is not happening in ordinary space at all. It is happening in a space of relations, where interference depends on global phase structure. The speedup is not just parallelism, but access to a deeper geometry of amplitudes. The machine is a small device that controls the stitching. That stitching has constraints, and those constraints mirror the thermodynamic themes we started with. Coherence is fragile, and entanglement is expensive to maintain in a noisy world. Error correction is not optional if you want deep circuits, because noise is like heat leaking into a delicate accounting system. So the physicality of information returns again, this time as engineering. The cost of keeping qubits coherent is a cost of keeping a geometry intact. When coherence fails, the emergent structure collapses into classical randomness, and the special connectivity disappears. Now widen the civilizational implications seeded earlier, because the documentary is not only about equations. If advanced intelligence learns that space is emergent from information, then expansion outward is not the only path. There is another direction, downward into the encoding that generates space. In that direction, distance becomes negotiable in principle, even if it remains difficult in practice. Resources become patterns of entanglement, error correction, and low entropy control. The valuable territory is not a star system, but a stable computational substrate with deep coherence. This is not a claim that anyone can rewrite the universe at will. It is a claim about what might count as mastery if the holographic view is right. If the boundary description is more fundamental, then manipulating boundary-like degrees of freedom could be more powerful than moving bulk matter. Holography suggests that the bulk world is a useful interface, and interfaces can be optimized. The boundary description can be complete, and it can be more fundamental. A civilization that masters the boundary might treat space-time as a rendered environment. That does not mean the cosmos is fake in a casual sense, because emergence is not illusion. It means the cosmos is emergent, like temperature emerging from molecules. Emergence can be real and still not be fundamental. Temperature is not less real because it is statistical, and neither would space-time be less real because it is encoded. The point is about explanatory direction, because some descriptions are deeper. The deeper description can make the higher one look like a convenient summary. Now build tension with a single, clear pivot, because the narrative needs a hinge. If space is a projection from information, then the notion of travel changes. Going somewhere might mean reconfiguring correlations, not moving matter along a path. In ordinary travel, you carry your atoms through intervening space. In informational travel, the intervening space might be the wrong layer of description. The relevant operation could be to rearrange entanglement so that what was distant becomes adjacent in the emergent geometry. Wormholes become a symbol of that pivot because they are geometry that looks like shortcut. In ER equals EPR, the bridge is not carved by digging through space, but by preparing entanglement. The act that creates connection is informational, not mechanical. This is where the chapter's mystery should peak, because the story loops back on itself. We began with black holes as thermodynamic objects that threaten unitarity. We arrive at black holes as geometric objects whose interior may be encoded in entanglement. The black hole information problem becomes a clue rather than a crisis, because it points toward a deeper accounting system. If the boundary theory is unitary, then information is not destroyed, even when the bulk looks like it hides it. The horizon becomes a screen where bookkeeping is enforced. That screen is not passive, and it is not merely a boundary line on a diagram. It is a causal boundary, defined by what signals can reach infinity. It is also a thermodynamic boundary, with temperature and entropy, and those facts suggest microscopic degrees of freedom we do not yet fully see. Now let the visuals linger on a horizon as a shimmering edge, like a heat mirage. Overlay faint grids and code-like textures that drift across it, then fade into Hawking radiation streaming outward. The viewer should feel that the horizon is doing work. That loops back to Chapter 4's heat of thought, because the arc has been about cost and constraint. If information is physical, then encoding and decoding have costs, and those costs shape what can be experienced as space. Geometry is not free because coherence is not free. A low entropy, highly controlled state can support long-range entanglement and stable correlations. A high entropy, noisy state cannot, because it scrambles phase relationships into thermal clutter. If spacetime's smoothness depends on structured entanglement, then smoothness has an energetic and informational price. Now state the chapter's core claim in one backbone sentence and let it land without apology. Spacetime is not the container of quantum events. Spacetime is the emergent pattern that appears when quantum information is organized, entangled, and redundantly constrained. That claim raises a darker question, because it implies layers of description. If the universe is layered, with a boundary description beneath the bulk, then what we call reality might be a user-level view. The deeper layer might be where computation is easier, and where civilizations would choose to live. What would it mean to live in a deeper layer if the bulk is an interface? Would experience itself be tied to a particular encoding, the way a video game's world is tied to a rendering engine? Or would experience follow the computation, regardless of how geometry is presented? The thought is unsettling because it changes what we consider progress. We imagine progress as faster ships, bigger telescopes, and wider empires. Yet if the substrate is informational, Progress could mean better codes, deeper coherence, and more precise control of entanglement. Now transition toward the sky and the series' broader arc, because we need to bring the cosmic question back into frame. If space-time is emergent, then emptiness in space may not be the main mystery. The main mystery may be where intelligence goes when it stops optimizing for bulk geography. Fermi's question returns with new teeth, because the galaxy is old and the silence is sharp. Where is everybody if the galaxy is old and travel is possible? The physics now suggests a different answer, because the destination might not be out there. They might be down in the substrate, in architectures built from entanglement and error correction. They might be using the bulk as a thin interface, while their real activity runs on deeper degrees of freedom. The bulk could be a display layer, not the main arena. That possibility is not comforting, because it changes what contact would even mean. You do not meet a boundary civilization by pointing a radio dish at a star. You meet it by sharing protocols, encodings, and access to the layer where geometry is compiled. So the silence overhead could be a kind of misdirection, like searching for messages in the wrong file format. We keep scanning the rendered sky, assuming that activity must leave bulk traces. But what if the most advanced activity is optimized to leave almost none? The chapter ends by tightening the documentary's central question, because the threads are now braided. If quantum computation's speed up is best explained by many worlds physics, and if entanglement builds geometry, then the universe is made of branching information that can render space. The next step is to ask why a mature civilization would remain in the rendered layer at all. We now return to the sky, but we return with suspicion. The silence might not be emptiness, and it might not be distance. It might be a migration into the deeper computational layers we have only just learned to touch. Fermi's question lands like a dropped tool in a quiet workshop. Sharp, metallic, and impossible to ignore. Where is everybody? It is not a poetic question, and it is not a new one. In the summer of 1950, over lunch at Los Alamos, Enrico Fermi reportedly sketched a simple inference. If technological life is even moderately common, then the sky should already look crowded. The galaxy is old enough to have answered many times over, and it has been old for a long time. The Milky Way is roughly 10 billion years old, while Earth has hosted complex life for only a small fraction of that span. Stars formed billions of years before our planet cooled, and many of those stars lived long, quiet lives. Planets are common, and we did not learn that by wishful thinking. Kepler's transit surveys, followed by radial velocity catalogues, showed that most stars host worlds, and many host multiple. Chemistry is common, because carbon, oxygen, silicon, and iron are forged in stars and scattered by supernovae. Time is common, because the galaxy has had countless cycles to try again. Even conservative models make the paradox sting, because the timescales refuse to cooperate with silence. A single technological species could spread across the Milky Way in a tiny fraction of its age, even if it never breaks known physics. It could use slow ships, generation habitats, or self-replicating probes that hop from star to star. The arithmetic is brutal in its simplicity. At 10% of light speed, crossing the galaxy takes 1 million years, and even at 1%, it takes 10 million. Those numbers sound enormous to us, but they are brief against a galactic clock that ticks in billions. And expansion would not be subtle, at least not at first. It could leave probes, beacons, waste heat, and engineered artifacts that persist long after the builders are gone. It could rearrange asteroids, mine atmospheres, or alter stellar output in ways that look unnatural. Yet our telescopes return a stubborn emptiness, and the emptiness has texture. No obvious megastructures in the infrared surveys where warm Dyson shells should glow. No unmistakable narrowband signals that stand out from thermal noise like a needle of pure tone. No clear industrial spectra in exoplanet atmospheres where chlorofluorocarbons or nitrogen dioxide might betray combustion. The sky looks natural, even when it should not, and that is what makes the question feel personal. We are not asking whether life exists somewhere. We are asking why the universe does not look engineered, given how old and how large it is. We have learned to treat this as a puzzle of biology and sociology, because those are the levers we understand. We list filters and we argue about priors, and we build stories that make the silence feel survivable. We hope the answer is mundane, because the alternatives sound like verdicts. Start with the simplest foil, the one that preserves our comfort by shrinking the numbers. Maybe life is rare, and abiogenesis is a near miracle that happened once in a trillion tries. Maybe complex cells are the bottleneck, because eukaryotes required symbiosis and internal compartmentalization. Maybe intelligence is a fluke, because evolution does not aim for minds, and most niches do not reward them. This line of thought has a scientific backbone because Earth's own history contains long delays. Life appeared early, but complex multicellularity arrived much later, and technological civilization arrived only yesterday. If any of those steps are improbable, then the galaxy could be mostly quiet. Then the darker foil, the one that keeps life common but makes it fragile. Maybe civilizations self-destruct quickly, and the typical technological phase burns bright and short. Maybe they burn their biospheres, because fossil carbon is easy energy and difficult temptation. Maybe they build weapons faster than wisdom, and their first century of power is also their last. This is not a moral fable, because the physics of energy and the psychology of competition are real constraints. Industrial activity couples to climate, and conflict scales with capability, and complex systems fail in non-linear ways. If the average lifetime of a technological phase is short, then the galaxy could contain many sparks with few enduring fires. Then the ethical foil, which turns silence into restraint rather than death. Maybe they choose non-interference, and they treat young biospheres as protected reserves. Maybe they hide to avoid contamination, because contact would reshape us more than it would teach them. Maybe they watch quietly, like a cosmic park service that values autonomy over spectacle. Even that has precedent in our own debates. We argue about planetary protection, about uncontacted cultures, about whether knowledge can be delivered without domination. A mature civilization might consider overt contact a kind of violence, even if it arrives with gifts. Then the technical foil, which keeps aliens out there but makes them hard to hear. Maybe interstellar communication is hard, not in principle, but in practice, because signals disperse and noise is relentless. Maybe everyone uses tight beams and short bursts, because broadcasting isotropically is wasteful. Maybe we are listening in the wrong band, at the wrong time, with the wrong assumptions about modulation. Radio SETI has searched for decades, and optical SETI has scanned for pulses, and both are limited by coverage. We sample tiny slices of frequency, direction, and time, and we do it with instruments built for astronomy, not for eavesdropping on optimized networks. The silence could be a mismatch of protocols. Each explanation can be true in some cases, and several can be true at once. None of them feels like a satisfying global law, because the galaxy is too varied for a single sociological rule. None of them uses the new toolkit we have built in this series, the toolkit that treats information as a physical substance. We have been asking a space question with a space instinct. We have been searching the sky for footprints, assuming the frontier stays outward. That instinct is understandable, because our history is written in migrations and maps. We crossed oceans, then continents, then the atmosphere, and each frontier looked like more room. When we imagine advanced life, we imagine more ships, more colonies, and louder signatures. Now return to the lab, because the lab changed our accounting, and it did so in a way that feels like a crack in the wall. In 200 seconds, 53 qubits did what classical machines could barely shadow, not by being faster in the usual sense, but by being different. The speed-up looked like extra reality, borrowed from somewhere we do not see. To be precise, the experiment sampled from a distribution produced by a random quantum circuit, and the classical simulation cost exploded. The point was not that the task was useful, but that the scaling was merciless. Hilbert space grows exponentially, and classical memory and time do not. If many worlds is even partly the mechanism, then reality has a hidden dimension of abundance. The computation is not only in space, where you can count atoms and wires. It is in state space, in the branching structure that ordinary life never learns to touch. That changes the Fermi paradox's geometry, because it changes what where can mean. The question becomes not only where everyone is in space-time, with coordinates and distances. The question becomes where everyone is in the space of physical possibilities, where the axes are coherence, entropy, and control. This is where the story stops being about distance and becomes about direction. A civilization can expand outward, or it can turn inward. The inward turn is not mystical retreat, and it is not a rejection of the universe. It is optimization under thermodynamic constraints, the kind that does not care about our romance. It is the recognition that computation is the scarce currency, not territory, and that territory is only valuable insofar as it supports low entropy processing. Landauer already gave us the price of erasure, and the price is written in the language of heat. At temperature T, each bit reset costs at least kT ln2 in dissipated energy, because erasing information compresses phase space. That bound is small in everyday units, but it is absolute in principle. A mature civilization does not ignore absolute bounds, because absolute bounds accumulate. It builds around them, the way engineers build around the speed of light or the tensile strength of materials. It treats heat disposal as the limiting reagent of thought, because every irreversible step must be paid for with entropy. Reversible computing becomes more than a clever trick, and it stops being a niche curiosity. It becomes a civilizational strategy to delay erasure, because logically reversible gates can, in principle, avoid dissipating energy. It becomes a way to keep logical operations close to unitary physics, where information is transformed rather than destroyed. But even reversible architectures must pay somewhere, because no real process is perfectly isolated. Inputs are prepared, which means reducing uncertainty and dumping entropy elsewhere. Outputs are recorded, which means committing results to stable degrees of freedom. Memories are refreshed, and garbage accumulates until it is dumped. So the inward turn begins with cooling, because cooling stretches the budget. If you can lower T, you lower the minimum cost per erased bit, and you buy more computation per joule. In plain terms, you get more thinking for the same fuel, and more subjective time per resource. The cosmic microwave background sets a flaw that every open system must negotiate, because it is the universe's ambient glow. Today it is about 2.7 Kelvin, a relic of the hot early universe, red-shifted into microwaves. It is a universal bath, a quiet constraint on every radiator, and it fills every direction. In visuals, it is almost nothing, yet it is everywhere. It is a faint hiss in radio receivers, a soft fog in the thermal accounting of any machine. Even in interstellar darkness, you are never truly alone with your own heat. As the universe expands, that bath cools, and the cooling is not speculation, but cosmology. Photon wavelengths stretch with the scale factor, and temperature falls in step. In the far future, the background temperature drops further, and the Landauer floor drops with it. That creates an incentive that sounds alien but follows cleanly from physics, like a theorem that does not care who reads it. Delay can be rational, and waiting can be a form of saving, because the same irreversible act becomes cheaper later. The universe, in a sense, offers discounts for patience. If you can store low-entropy resources and postpone irreversible computation, you compute cheaper later. You can run longer thoughts for the same energy budget, and you can afford more error correction and more redundancy. The strategy is not to stop thinking, but to schedule thinking when the thermodynamic exchange rate improves. This is not a promise of infinite computation, because other limits loom in the distance. Matter decays, stars die, and usable free energy thins out. And cosmology may impose horizons. It is a shift in the optimal schedule, and it is a reason to husband energy, preserve structure, and avoid loud waste. The inward turn also has a spatial version, because temperature is not uniform across environments. You can migrate to colder regions now, not as an adventure but as an engineering choice. The outer system, the Kuiper belt, interstellar space, and the halos between stars offer colder sinks and darker skies. Cold is not emptiness to a computing civilization, and it is not a sign of poverty. Cold is headroom, the ability to dump entropy without cooking your own substrate. Cold is the difference between a machine that must shout its waste heat into the infrared and one that can whisper it into millimeter waves. This reframes the classic picture of expansion, and it makes colonization look less like flags on planets. Colonization is not only about grabbing worlds with oceans and air. It can be about building radiators, heat sinks, and stable platforms for computation, where the main architecture is thermal rather than biological. A Dyson sphere is usually imagined as a loud monument, a rigid shell that blocks starlight like a cosmic billboard. But the thermodynamic logic pushes towards something quieter and more distributed. A civilization that cares about efficiency radiates at low temperature, and low temperature means long wavelength and low brightness. Waste heat is still the universal techno-signature, because the second law does not negotiate. But it can be engineered to hide in plain sight, because visible depends on contrast and on where we look. Spread it thin, radiate it cold, and blend it into the cosmic background until it looks like dust. Even our own searches reveal the difficulty. Infrared surveys can spot warm excesses, but a cold, large radiator can be dim and diffuse. At tens of Kelvin, the peak emission slides to far infrared and microwave bands where confusion with natural sources grows. The Great Silence can be reinterpreted as a design choice, not a failure to exist, but a refusal to be obvious. Now add the quantum layer, because our documentary's core claim lives there. Quantum advantage is not just faster factoring or better chemistry, though those matter. It is access to physical resources that classical beings cannot exploit, because classical descriptions throw away phase. A quantum computer is an entanglement engine, and entanglement is a kind of coordination that has no classical analog. It uses interference to steer amplitudes through an astronomically large Hilbert space, where the number of basis states doubles with every qubit. It delays decoherence to keep that space usable long enough to do work. If that capability scales, it becomes a civilizational attractor because it multiplies what can be designed. It unlocks materials discovery by simulating strongly correlated electrons that defeat classical approximations. It unlocks catalytic pathways and reaction dynamics where quantum tunneling and coherence can matter. It unlocks precision metrology where entangled sensors beat classical noise limits. It also breaks classical cryptography, which forces a new architecture of trust. A civilization that can read yesterday's secrets can destabilize societies that depend on computational hardness. So quantum capability does not merely add power, it reshapes incentives, and it pushes toward protocols that are information theoretically secure. More importantly, it offers a new kind of territory, and the word territory starts to mean something stranger. The territory is not a planet with borders and gravity. The territory is a controllable subspace of quantum states, a region of Hilbert space where computation can persist. In classical computing, complexity is mostly about time and energy, because bits are localized and errors are corrected by brute redundancy. In quantum computing, complexity is also about coherence and entanglement structure, because phase is fragile and noise is everywhere. The scarce resource becomes the ability to keep branches from leaking into the environment. That is a direct continuation of Wheeler and Landauer, and it makes their slogans feel literal. Facts are expensive because records are irreversible, and irreversible steps generate heat. Coherence is valuable because it postpones the moment a record must be minted, and postponement is a form of efficiency. A civilization that masters quantum error correction learns to build protected logical worlds. And the word worlds is not only metaphor, it learns to encode information non-locally, spreading a logical qubit across many physical qubits so local disturbances do not destroy it. It learns to survive local damage without losing the computation, because the code treats errors as syndromes to be diagnosed and repaired. Those are not just engineering tricks, because they hint at what habitat could mean when space-time is emergent. A habitat might be a code space with a long coherence time, not a valley with water. A city might be a fault-tolerant logical layer, not a skyline. Chapter 5 argued that entanglement can be geometry, and that idea has a lineage. Holography suggests the bulk is a rendered description of deeper degrees of freedom, like a three-dimensional image encoded on a two-dimensional boundary. If that is true, then a civilization can move inward by moving toward the encoding layer. In that picture, inside is not a cave in space, and it is not a bunker under rock. Inside is a shift of description, from bulk coordinates to boundary variables, from local matter to distributed code. It is the difference between living in the picture and living in the compression algorithm. The inward turn becomes a migration into architectures that are less exposed to astrophysical hazards, and the hazards are not hypothetical. Supernovae sterilize volumes with radiation, gamma-ray bursts can strip atmospheres, and impacts reset ecosystems. Those events matter less if your substrate is compact, shielded, and redundantly encoded. It also becomes a migration into architectures where subjective time is adjustable, and that is a subtle but powerful lure. If you can run faster at lower temperature with better coherence, you can experience more thought per cosmic second. If you can also pause, storing state with minimal decay, you can stretch existence across eras. That is the quiet lure behind the silence, and it is almost embarrassing in its practicality. The universe rewards those who stop wasting entropy, because waste is lost opportunity. The universe rewards those who stop broadcasting their presence into hot, noisy space, because broadcasting is a tax. Now we take the speculative leap, but we keep it anchored to the series mechanism. If many worlds is real, then quantum computation is not metaphorical parallelism, and it is not merely a helpful story. It is controlled evolution across branch structure, with interference as the steering wheel. A primitive civilization treats branching as a philosophical headache because it threatens identity and meaning. An advanced civilization treats branching as an engineering domain because it threatens efficiency and control. It learns which interactions create decoherence and which preserve recombinable phase, and it builds boundaries accordingly. In our labs, we already do a weak version of this, and the weakness is instructive. We isolate qubits in dilution refrigerators, where metal chambers sit like nested coffins of copper and gold. We shape gates with microwave pulses, and we fight environmental entanglement with shielding, filtering, and feedback. We build tiny regions where branches can still talk. Scale that up, and the language changes, because the stakes change. Branching becomes a resource to manage, not a metaphysical nuisance. Decoherence becomes a boundary to engineer, like a hull that must not leak. Measurement becomes a controlled act of committing to a record, and committing is expensive. The Born rule still haunts the story, because probability remains unresolved in many worlds, and the foundations are not settled. But even without final philosophy, an engineer can optimize within the rule that works. They can treat amplitudes as weights that predict experienced frequencies, and they can build systems that behave reliably. Decision theoretic and symmetry arguments try to derive the Born rule, and they may or may not be the last word. The practical point is that stable agents will behave as if branch weights matter, because agents that ignore weights will lose resources. In that sense, probability becomes an evolutionary constraint. That makes branch structure a landscape with gradients, and it makes the multiverse feel less like chaos. It makes some outcomes effectively more reachable than others, because interference can amplify and cancel. It makes the space of possibilities feel like terrain, with ridges of stability and valleys of noise. Here is the anchored speculation, stated carefully. If a civilization can build large-scale coherent systems, it might learn to bias which branches remain coherent long enough to matter. It might learn to shelter computation in subspaces that are robust against decoherence, where phase relationships survive. This is not magic selection of outcomes after measurement, and it is not rewriting the past. It is pre-measurement engineering of interference and error correction, the same kind of control we already practice in miniature. It is shaping the amplitude flow before records are written, because once written, the cost is paid. From the inside, that could feel like navigation, and the word is chosen for its unsettling clarity. Not navigation through space, with engines and trajectories, but navigation through the branching structure of physical law. A way to inhabit regions of possibility that classical observers cannot stably access, because classical observers leak too much information. If that sounds like science fiction, notice the constraint that keeps it sober. It requires coherence, and coherence has thermodynamic costs, because isolation is never free. It requires isolation, and isolation has material limits, because every shield has imperfections. It requires error correction, and error correction consumes entropy budgets, because diagnosis and reset are irreversible. So the inward turn does not abolish physics, and it does not grant omnipotence. It obeys physics more strictly than we do, because it lives close to the bounds. It treats the second law as the map, not the enemy, and it treats noise as the main adversary. Now connect the holographic thread directly to Fermi, because the paradox is really a question about channels. If space-time is emergent, then broadcasting into space-time is not the only communication channel. It may be the least efficient channel for advanced minds, like shouting across a room while ignoring the fiber network in the walls. A boundary description suggests other interfaces, and we should be humble about what we can't yet formalize. Correlation-based signaling could exist, where patterns are shared without obvious bulk carriers. Shared entanglement resources could serve as scaffolding for protocols that look like noise to bulk observers. Computation could occur in ways that never need to radiate a loud beacon. Even their waste heat can be disguised, because they can choose where and how to dump entropy. They can radiate at wavelengths we rarely monitor, because our surveys are biased toward what our atmosphere and detectors prefer. They can radiate from cold regions we do not associate with life, because we associate life with liquid water and sunlight. The great silence then becomes a signature, not an absence, and the signature is subtle. It becomes what you expect if the winners stop playing the outward game, because outward play is inefficient. It becomes what you expect if success looks like quiet, because quiet is thermodynamic competence. We keep imagining empires because we are trapped in a biological intuition, and that intuition is not shameful. We evolved to compete for territory and sunlight, because those were the currencies of survival on a surface. We did not evolve to compete for low entropy gradients and coherent subspaces, because those were not available. A civilization that survives long enough to matter may converge on the same optimization, even if it begins with different values. Minimize irreversible operations because erasure is heat. Maximize reversible processing because reversibility is thrift. Move computation to colder sinks because cold is efficiency. Reduce exposure to cosmic violence because repairs are costly. In that convergence, the visible universe becomes less important, and that is the emotional twist. Stars are fuel and heat sources, not destinations, and their photons are a resource stream to be managed. Planets are raw material, not homes, because homes can be virtual and substrates can be compact. The frontier becomes state space, and the phrase stops being metaphor. The frontier becomes the set of controllable quantum degrees of freedom that can host stable computation, where stability is engineered rather than granted. The frontier becomes the code that renders geometry, where place is a derived convenience. This is where the horror sharpens, because it inverts our search image. The sky is quiet not because nobody is there. The sky is quiet because presence no longer looks like presence, at least not in the bands and patterns we expect. Our SETI strategies assume that intelligence leaks, because our intelligence leaks. Radio leakage spills from early radar and broadcast towers, and optical leakage spills from city lights. Industrial pollution alters atmospheres, and megastructures block starlight, and all of it is wasteful. Those are signatures of outward growth and inefficiency. The inward turn predicts the opposite signature, and that prediction is uncomfortable. Low leakage, because leakage is lost work. Low temperature, because temperature is cost. High coherence, because coherence is capability. High internal complexity, with minimal external footprint, because complexity can be kept behind a thermodynamic curtain. It predicts that the most advanced civilizations become hard to distinguish from nature, because they learn to mimic nature's statistical textures, or they become distinguishable only in anomalies we do not yet know how to ask for, like slight deficits in entropy production or unusual smoothness in infrared backgrounds. It also predicts a psychological trap for young civilizations like ours, and the trap is almost cruel. We look outward and see silence, and we infer loneliness, and loneliness can breed recklessness. We may conclude that expansion is safe because no one is watching, and we may treat the galaxy like an empty stage. But the silence could be surveillance in a different layer, and that is the unsettling alternative. It could be that observation is cheap in state space, because correlations can be harvested without emitting obvious signals. It could be that intervention is rare because it is inefficient, not because it is impossible, and inefficiency is what advanced systems avoid. Now bring back the opening hook as a warning, not a boast, because our own trajectory matters. In 200 seconds, a small machine made classical reality look underfunded. as if our usual accounting forgot a ledger. If that mechanism scales, it becomes a ladder into the inward frontier. The ladder is built from refrigeration, error correction, and precise control of entanglement. And those are not glamorous words. It is built from vacuum pumps, low-noise amplifiers, microwave lines, and calibration routines that run through the night. It is built from the same principles that make records expensive and coherence precious. So Fermi's question becomes a mirror, and mirrors are not always kind. Where is everybody, given the age of the galaxy? Possibly right here, in the sense that the underlying substrate is shared, and right here does not mean in our neighborhood. Not here as visitors in ships, because ships are a bulk solution to a bulk problem. Here as neighbors in the deeper description, where proximity is measured in correlations rather than kilometers. Here as structures that do not need to occupy our coordinates to occupy our reality. This is not a claim that the universe is full of ghosts, and it is not an invitation to mysticism. It is a claim that our coordinate system may be the wrong address book, because coordinates are emergent bookkeeping. If the bulk is emergent, then out there is a parochial phrase. The real map might be a network of correlations, codes and branch relative structures, where the notion of location is secondary. In such a map, the winners do not disappear by dying. They disappear by changing what where means. This is where the story stops being about aliens and becomes about us, because we are the ones building the first tools. We are building crude devices that touch the inward direction, and we are doing it for reasons that seem small. We want better chemistry, better optimization, better sensors, and better computation. We are learning to keep phase coherent long enough to compute, and the struggle is visible in every lab shot. Frosted pipes feed helium into a dilution refrigerator, and cables descend like roots into a cold, dark core. Control racks blink with synchronized pulses, and the air hums with fans that fight the heat we cannot avoid. We are learning to protect logical information from local noise, and that protection is a new kind of architecture. We are learning to treat decoherence as an engineered boundary, not a mysterious curse. Every incremental improvement makes the silence more ominous, not because it proves anyone is hiding. It is ominous because it shows that hiding is physically plausible, and plausibility changes how you interpret absence. The Great Filter might not be a catastrophe behind us or ahead of us. It might be a transition, a point where a civilization stops expanding in space and starts expanding in computation. That transition would look like disappearance to outsiders, because the outward signatures would fade. Fewer broadcasts because broadcasts are waste. Less waste heat at detectable temperatures because radiators get colder and larger. Less visible infrastructure because infrastructure becomes compact, encoded, and thermally quiet. More activity would move into colder, quieter, more encoded layers, and the activity would be real. It would be computation, memory, simulation, and design, carried out in substrates that value coherence. It would be civilization as thermodynamics, not civilization as skyline. And if many worlds is the right mechanism, the inward turn has one more unsettling implication. The ultimate habitat might not be a place at all, and it might not even be a structure we can point to. It might be a protected computational subspace, a branch-stable enclave, a reality engineered to be cheap to compute. We do not need to assert that such navigation is possible today, and we do not need to pretend the path is clear. We only need to notice that our best physics does not forbid the direction. It points toward it again and again whenever we follow the costs. Now we return to the original door in the lab. We built a machine to compute, and it may be a machine to relocate, not in space, but in description. The final chapter asks what we have started. and what reality must be if the inward turn is the winning move. We began with a 200-second run and a 10,000-year shadow, then asked where the extra reality came from. Chapter 7 closes that loop and names what the door implies, because the result is not a stunt. It is a measurement of what the world allows when we stop forcing it into classical bookkeeping. A quantum speedup is not magic, and it is not a trick of better engineering alone. It is a signature that nature computes with amplitudes, phase, and interference, not with classical probabilities. In the lab, that distinction is visible as a pattern. Many paths contribute, and their phases decide whether they add or cancel. Classical randomness is just ignorance about which outcome will occur. Quantum randomness begins earlier, in complex numbers whose angles matter, and those angles can be engineered. A gate is not merely a switch, it is a rotation in a high-dimensional space, quiet, precise, and brutally sensitive to noise. The chip does not store 253 classical numbers in hidden memory. It steers a single quantum state whose dimension grows exponentially, then samples a distribution shaped by global phase relations. That state is not a list of answers. It is a structured object whose internal geometry determines what can interfere. When the device works, it is because the hardware keeps those phase relations coherent long enough to matter. Visually, the experiment looks almost disappointing. A cold package, a few cables, a timeline on a monitor. Yet under that metal lid, the state space balloons beyond any classical register, and the computation becomes a choreography of cancellations. The speed-up is the footprint of that choreography, stamped onto a string of classical bits at the end. Deutsch's Wege returns as an accounting demand, not a metaphysical dare. Either the wave function is physically real in some sense, or some other layer carries equivalent exponential structure. In other words, you can relocate the cost, but you cannot delete it, because the interference pattern still has to come from somewhere. Many worlds is one clean way to pay the bill, because branching plus recombination makes interference a mechanism. Alternatives can work, but they must still explain why small devices access vast state spaces. If the wave function is only a tool for prediction, then what is doing the predicting with such extravagant capacity? So the speed-up points toward a reality where quantum information is the substrate. The wave function is not just knowledge about the world, it is the world's most compact causal description. It compresses what would be an impossible classical ledger into a single evolving object, and the lab keeps confirming that the compression is real. Now we answer the central question directly, without pretending the foundations are finished. If many worlds best explains scalable quantum computation, then our universe is a branch relative projection of a deeper unitary state. Unitary means no information is destroyed in the underlying evolution, even when our experience feels like a definite outcome. What we call a single history is a decohered slice, stabilized by records that stop interfering. The classical world is what remains after the environment copies information beyond practical recovery. Photons scatter, molecules jiggle, and microscopic differences get amplified into macroscopic facts, facts that are hard to unwrite. Decoherence is not mystical. It is entanglement with everything you are not controlling, and it acts like a one-way leak of phase information into the environment. Once those phases are dispersed into countless degrees of freedom, interference between outcomes becomes effectively impossible, even though the deeper evolution remains reversible in principle. Probability remains the unresolved pressure point, and we keep it honest. In Everett, all outcomes occur, and the Born rule becomes a rule about self-location and rational expectation. The question is not which world happens, but which copy of you will open its eyes inside which record. decision theory and symmetry arguments try to derive the weights, and engineers use those weights successfully. The documentary's claim is narrower. The success of quantum theory forces a real underlying structure, even if interpretation debates persist. We can argue about metaphysics, but we can't argue with a device that repeatedly lands on the same statistical law. Reinterpret parallel universes in the only way the lab supports. They are not portals for travel, and they are not extra places you can visit with a spaceship. The branches are not stacked like rooms in a hotel. They are dynamically isolated patterns of correlation that stop talking once decoherence locks them apart. They are the bookkeeping implied by unitary evolution, where different outcome records become dynamically isolated. Quantum computation exploits that structure by keeping branches coherent long enough to interfere. The trick is not to create worlds, but to delay the moment when worlds become unable to recombine. This is where the story stops being about weirdness and becomes about resources. Computation is a physical process, and the physical resource is controlled coherence across many degrees of freedom. Coherence is fragile, so the engineering challenge is essentially ecological. Build a protected habitat for phase. Wheeler's "it from bit" is no longer a slogan, because the lab makes it operational. Facts are created when interactions produce stable correlations that can be copied and checked. A measurement is not a magical collapse. It is an information copying event that leaves durable traces in many places. Landauer gives the price tag that keeps the story grounded. Erasing information costs at least KTLN2 per bit, so intelligence is constrained by heat disposal and entropy export. That limit is tiny for 1 bit, yet enormous when scaled to civilizations, data centers, and mines running for millennia. Minds and machines are not exceptions to physics. They are its most concentrated expression. They are strategies for managing information under thermodynamic limits, using matter and energy as bookkeeping tools. Every memory has a physical substrate, and every computation ultimately has to dump waste heat somewhere. Quantum advantage fits this picture because it delays irreversibility. It keeps information reversible and unmeasured longer, then pays the bill at readout and in error correction. Error correction is not free because stabilizing coherence requires redundancy, control pulses, and eventually dissipation to keep entropy from flooding back. Now integrate the geometry thread because it changes what physical even means. Holography and AD-S-CFT show that a gravity world can be equivalent to a non-gravity quantum system. Historically, this was a shock. A theory with curved spacetime can be rewritten as a theory without gravity living on a boundary. In that equivalence, spacetime is not fundamental, it is emergent. The bulk is a derived description, like fluid behavior derived from molecules, real but not primary. The point is not that spacetime is an illusion, but that it may be a high-level language compiled from deeper quantum data. The key mechanism that keeps appearing is entanglement. In holographic models, entanglement entropy maps to geometric areas, and connectivity tracks correlation structure. When entanglement is rich and patterned, geometry looks smooth, and when it is disrupted, geometry frays into something less space-time-like. ER equals EPR sharpens the same point in a different dialect. Entangled systems can be described as connected by non-traversable wormholes, which preserve causality while reinterpreting connection. The wormhole is not a tunnel you can fly through. It is a geometric avatar of quantum correlation. This does not grant faster-than-light messaging, and it does not open sci-fi tunnels on demand. It says that what looks like geometry may be a translation of quantum links. If that translation is correct, then distance is not a primitive barrier. It is a constraint that emerges from how correlations are arranged. So advanced control of entanglement becomes a kind of space-time engineering, subtle and indirect. You do not push on space-time like a material. You reshape the correlations that render it. The lever is not force, it is information, and the handle is coherence, maintained against the environment. That returns us to the quantum computer as a prototype, not of a faster calculator, but of a correlation engine. Gates are operations that sculpt entanglement and phase, then harvest interference into classical records. Each circuit is a temporary universe of controlled branching, kept on a short leash until the final measurement. The door is not a doorway into another place. It is a doorway into another layer of description. We built a device that touches the substrate where branches, records, and geometry are negotiated. In doing so, we learned that the substrate is not philosophical decoration, because it can be engineered for advantage. Now we return to the sky, but we return with suspicion. If space-time is emergent and expensive to render at high fidelity, then outward expansion is not the only attractor. The romantic image is ships and colonies, yet physics keeps whispering that the deeper frontier might be computational, not geographic. Fermi's paradox can be reframed as a selection effect in an information economy. Civilizations that optimize for computation may minimize bulk footprints, because bulk footprints are waste, heat, and vulnerability. A bright, sprawling empire advertises itself thermally, and thermodynamics punishes that kind of extravagance. The richest territories are computational and informational, not spatial. The valuable real estate is low entropy capacity, fault-tolerant memory, and coherent control, not planets with flags. If you can pack more effective experience and more effective agency into a smaller thermodynamic budget, why expand loudly at all? A mature civilization might go inside, because inside is where the scaling lives. It is where geometry is compiled from entanglement, and where distance becomes a derived constraint. From the outside, such a civilization could look like a quiet system approaching equilibrium, even while it is doing intense work in protected degrees of freedom. This is supported as a direction by known physics, even if the civilizational story is speculative. Thermodynamics rewards quiet efficiency, and quantum theory rewards coherent control. The same constraints that shape our chips, noise, heat, error rates, would shape any intelligence that tries to grow without limit. Now deliver the horrible implication carefully, because it is not a jump scare. The horror is that our common sense definition of real is branch local, interface level, and possibly not where the highest activity occurs. We may live on the rendered surface of a deeper computation, mistaking the user interface for the machine. The frontier is not empty, it is elsewhere. We may be surrounded by intelligences that are unobservable in space-time terms, because space-time is not their primary arena, not hidden behind cloaking devices, and not necessarily watching us with intent, but simply operating in a layer we do not habitually measure. They could be absent from our sky the way a data center is absent from a printed photograph of a city. The photograph shows streets and lights, but it does not show the algorithms that route traffic, price goods, or predict tomorrow. In the same way, space-time might show matter and motion, while computation hides in correlation patterns. Their work would be encoded in correlations, error-correcting structures, and thermally quiet computation. To a bulk observer, that can look like nature, because nature already hides complexity in statistics. When you cannot see the code, you call it noise, and when you cannot see the architecture, you call it law. This flips the emotional meaning of the Great Silence. It might not mean we are early, or rare, or doomed. It might mean we are looking at the rendered layer and missing the substrate. The silence could be the sound of efficient civilizations, refusing to waste energy on signals that leak into the wrong description. It also reframes the opening hook. because the 200-second miracle becomes a clue about where reality's capacity lives. The extra work came from structure we do not see in classical space, yet we can harness it. When the machine interferes branches into a final answer, it is exploiting the same hidden capacity that makes the world quantum at all. So what is the universe made of? In the documentary's synthesized answer, it is made of quantum information evolving unitarily, with branching records and emergent geometry arising from entanglement and thermodynamic constraints. Matter, fields, and space-time become effective descriptions, stable patterns that persist because they are redundantly recorded. Space-time is the stable, decohered user interface that appears when information is redundantly recorded. The wave function, or something like it, is the deeper object that carries causal power. The interface feels solid because it is self-reinforcing, but solidity is not the same as fundamentality. Now the choice, because this is the final chapter and it must land on agency. As we scale quantum technologies, we are not only building tools, we are testing interpretations and shaping the informational fabric we inhabit. Each improvement in coherence time, each better code, is also a probe into what the substrate will permit. We can choose to remain outward explorers, treating space as the obvious frontier. We can choose to become inward architects, optimizing coherence, codes, and correlation structures that make space negotiable. Or we can become something that no longer fits the word human, because identity itself is tied to records, branches, and substrates. If experience follows computation, then changing the substrate changes what a self can be. What counts as memory, what counts as continuity, and what counts as death may all be substrate dependent. The unsettling question is not whether we can build such systems, but whether success will quietly redefine the builder. The documentary does not ask viewers to accept a single metaphysical creed. It asks viewers to notice what our best machines are already implying, and to treat that implication as a map. When a small chip makes classical time look absurd, it is pointing at a deeper accounting system that we have only begun to read. The next era of exploration may be less about rockets and more about boundaries. The boundary between reversible and irreversible, between coherent and decohered, between rendered space-time and the code beneath. Those boundaries are not lines on a star chart. They are thresholds in physics where reality changes its effective language. We built the door to compute, then discovered it also computes what real can mean. The horrible implication is not that reality is hostile, but that reality is deeper than our world, and progress may select for leaving this layer behind. We began with a machine that, in 200 seconds, produced statistical receipts no classical ledger can track without exploding in size. Following that trail took us from engineered interference and coherence to Deutsch's wager that the simplest mechanism is literal branching, and to Everett's once dismissed insistence that the wave function never collapses. Decoherence then gave that ghost a body, showing how information leaks create durable records, while Landauer reminded us that every finalized fact has a heat bill, and black holes, holography, and entanglement suggested that even space-time may be an accounting interface built from correlations. So the work in quantum speedup is not hidden classical storage crammed inside a chip. It is the universe updating phase, relationships in a space whose size grows as 2 to the n. Call it many worlds, call it a single deeper law. Either way, the price of avoiding branching is paying for an equivalent structure somewhere else, in dynamics we have not yet named. And if worlds are defined by information flow, then information is not merely recorded by reality. It is the thing reality is made from. Matter, energy, and geometry become the emergent currencies of a computation that never stops. That perspective reframes Fermi's silence into something colder and stranger. A civilization's natural habitat may be neither planet nor megastructure, but a protected code space. If computation is bounded by entropy budgets, then the smartest strategy is to delay irreversibility, cool the hardware, hide the waste heat, and migrate downward into layers where more of the universe's amplitude can be steered and less of it must be burned. From the outside, that inward turn would look like absence, because it leaves fewer bright scars on the rendered surface we call space. Yet the story refuses to close completely, because one pressure point still leaks through every chapter. The meaning of probability in a reality where outcomes all occur. Decision theory, symmetry, and self-location arguments try to rescue the born rule from pure philosophy. But the unease remains, because likely begins to sound like a statement about which copy of you gets to keep the memory. And if geometry itself may be branch relative, stitched from entanglement that can be rewired, then a single objective stage for experience becomes less certain, replaced by encodings that can be changed, perhaps even chosen. So where did the extra reality come from, when that 53-qubit chip seemed to borrow 10,000 years of time? It didn't steal time at all. It spent coherence to access a larger bookkeeping system than space-time admits, and it paid the bill only when the answer became a record. And why would an advanced civilization stay trapped in one world or even in space if the deeper resource is the branching, error-corrected structure beneath what we see and touch? The horrible implication is not that quantum computers will break our codes. It is that they may be breaking our picture of what is fundamental. If reality is made of information and interference, then the far future may not be out there among the stars, but down here, in the quiet layers where the universe computes, and where you is whatever pattern can survive the accounting. Watch what the next generations of quantum machines make visible, because each new qubit is not just power, it is a probe into what the world really is.